In the summer of 1977, while disco rhythms pulsed across Earth and home computers were still a novelty, two slender spacecraft were being prepared for a journey no human or machine had ever attempted. They would not orbit Earth, nor loop endlessly around the Sunday. They would leave. Their mission was to explore the farthest planets and, if the physics allowed, continue into the unknown. These were Voyager 1 and Voyager 2, twin probes designed to push the limits of engineering, curiosity, and endurance. If the far reaches of space and the secrets they hold captivate you, subscribe now. Join us as we follow humanity's most daring journey into the unknown. The Voyager project began with a mathematical discovery. In the early 1960 seconds, researchers at NASA's Jet Propulsion Laboratory, or JPL, identified a rare planetary alignment, one that occurs about once every 176 years. Jupiter, Saturn, Uranus, and Neptune would be aligned so that a spacecraft could use each planet's gravity to accelerate toward the next, significantly reducing fuel requirement. This technique, called a gravity assist, made it possible for a spacecraft to reach the outer solar system in roughly a decade. By the early 1970 seconds, NASA had turned this concept into the Voyager program, an ambitious twin mission designed to seize this narrow celestial opportunity. Each spacecraft was built around the same design, a 3.7-meter high-gain antenna for communication, 3 long booms for instruments, and a power source that relied not on solar panels useless in the dim outer reaches, but on radioisotope thermoelectric generators, or RTGs. These RTGs converted heat from decaying plutonium-238 into electricity, providing a steady trickle of power that would last decades. Engineers knew that as long as the instruments worked and the RTGs produced power, Voyager would keep talking to Earth. The spacecraft carried 10 scientific instruments, each designed to study a different aspect of the outer solar system. Cameras to photograph planets and moons, magnetometers to detect magnetic fields, plasma spectrometers to study charged particles, cosmic ray detectors to measure high-energy radiation. Every sensor was built with the resilience to survive intense, cold, cosmic rays and long periods of silence. Voyager's designers included a secondary objective: to carry a cultural artifact representing Earth. Under the leadership of astronomer Carl Sagan, a small team created the Golden Record, a gold-plated copper phonograph containing sounds and images of Earth, including greetings in 55 languages, natural sounds, and musical selections. The record's cover included diagrams explaining its playback method and the origin of the spacecraft. Voyager 2 launched first on the 20th of August 1977, followed by Voyager 1 on September 5. Although named sequentially, Voyager 1's faster trajectory would overtake its twin and reach Jupiter first. Each launch used a Titan III Centaur rocket, the most powerful launch vehicle of its era, to hurl the 722-kilogram probes on an escape path from Earth. Once free of Earth's gravity, they began a voyage that no one could control beyond simple course corrections and software commands sent from billions of kilometers away. At first, the Voyager's mission seemed straightforward: fly past Jupiter and Saturn, photograph their moons, study their atmospheres, and measure their magnetic fields. Yet what followed redefined humanity's understanding of the solar system. When Voyager 1 approached Jupiter in 1979, its cameras captured images of swirling clouds larger than Earth, lightning storms, and the Great Red Spot, an enormous hurricane that had raged for centuries. Then came the real surprise. Io, one of Jupiter's moons, was discovered to be volcanically active. No one had ever observed volcanoes beyond Earth before. Voyager had turned what was thought to be a cold, dead world into a theatre of fire and motion. Voyager 2 followed, confirming and expanding on those discoveries, then moved on towards Saturn, where it revealed the complexity of the planet's rings, billions of particles orbiting in delicate bands and gaps, shaped by gravitational resonances. It also discovered new moons and helped scientists understand that the outer planets were not isolated giants, but part of a dynamic system, constantly reshaping itself. By 1981, Voyager 1 had completed its main mission. Its flight path sent it upward and away from the plane of the planets, out of the ecliptic, on a trajectory toward interstellar space. Voyager 2 continued on, visiting Uranus in 1986 and Neptune in 1989, becoming the only spacecraft ever to visit those worlds. When Voyager 2 flew past Neptune, it photographed a blue world whipped by supersonic winds and a dark storm system eerily reminiscent of Jupiter's. After that encounter, both probes were headed into deep space. Their planetary work was done, but their greatest discoveries lay ahead. In the decades that followed, the Voyagers transitioned from planetary explorers to interstellar pathfinders. Scientists at JPL developed what they called the Voyager Interstellar Mission, or VIM, extending the probe's objectives to study the outer boundary of the Sun's influence. The Sun emits a constant flow of charged particles called the solar wind, which streams outward in all directions at hundreds of kilometers per second. This wind creates a vast bubble around the Sun and its planets, known as the heliosphere. The edge of this bubble marks the point where the solar wind's strength is balanced by the pressure of the interstellar medium, the thin soup of gas, dust, and magnetic fields that fills the space between stars. For decades, astronomers had theorized what this boundary might look like, but no probe had ever reached it. The Voyagers, moving at about 17 kilometers per second, were our best chance to find out. As they journeyed farther, their instruments began to sense changes in the environment. The solar wind slowed, magnetic fields fluctuated, and cosmic rays normally deflected by the heliosphere began to increase in number. These were the first hints that the spacecraft were approaching the outermost regions of the Sun's domain. Communication with the Voyagers required precision that bordered on the miraculous. The spacecraft transmitted data using a 23-watt radio transmitter about the power of a refrigerator light bulb. Yet Earth's Deep Space Network, or DSN, a global array of massive antennas, could detect those faint whispers across billions of kilometers. The signals took over 20 hours to reach Earth, meaning that every command and response was separated by almost 2 days. Engineers had to plan each maneuver carefully, knowing that a simple error could end contact forever. As the years passed, the Voyagers became cultural icons. They had traveled farther than any object ever built by humans, and yet they kept working. The spacecraft entered the 2000s still alive, still measuring, still reporting. By August 2012, Voyager 1 crossed a threshold that scientists had awaited for decades: the heliopause, where the solar wind's influence gives way to the interstellar medium. It was the first human-made object to enter interstellar space. Voyager 2 followed in November 2018, confirming the existence of this invisible frontier. But even as they moved beyond the Sun's reach, something unexpected awaited them. Leaving the planets behind, the long drift to the frontier. When Voyager 2 completed its flyby of Neptune, the last images it sent home were of a crescent world fading into darkness. After 12 years of planetary observations, both Voyager spacecraft were powered down to save energy on their cameras. From this point onward, Voyager instruments were configured to study charged particles, cosmic rays, and magnetic fields at the outer edges of the solar system. At the time, Voyager 1 was nearly 4 billion miles, or 6.4 billion kilometers from Earth, traveling northward out of the plane of the planets. Voyager 2, lagging behind and slightly south of the ecliptic, trailed by roughly 1.5 billion miles. Though separated by a gulf wider than the distance between the Sun and Saturn, the two probes were united in purpose. Their new assignment formally announced in 1990, was the Voyager interstellar mission to study the outer heliosphere, the vast region where the solar wind interacts with the galaxy beyond. The heliosphere is a colossal bubble carved out of the interstellar medium by the solar wind, a stream of charged particles, mainly protons and electrons, flowing from the Sun at about 400 kilometers per second near Earth's orbit. As the Voyagers journeyed outward, scientists expected to find signs that this wind was slowing and compressing against the thin gas that fills interstellar space. But no one knew exactly where the Sun's influence ended. Estimates placed the edge anywhere from 90 to 200 astronomical units, or AU, from the Sun that's between 13 and 30 billion kilometers, a vast range that could take decades to traverse. From 1989 onward, the spacecraft became instruments of persistence. Each transmitted roughly 160 bits of data per second slower than the earliest dial-up modems through antennas that had to be pointed with exquisite precision. The Deep Space Network, or DSN, consisting of 70-meter radio dishes in California's Mojave Desert, near Madrid in Spain and near Canberra in Australia, listened constantly. Engineers used a technique called radio interferometry to combine signals from multiple antennas, effectively increasing their sensitivity. Even so, Voyager's signal at these distances was less than a billionth the power of a watch battery by the time it reached Earth. To conserve energy, NASA's flight controllers shut down non-essential systems. The cameras were turned off in 1990 after one last sequence of photographs, a portrait of the solar system. At 3.7 billion miles from the Sun, Voyager 1 captured Earth as a tiny speck suspended in darkness. Following this, the spacecraft continued operating instruments designed to measure plasma, cosmic rays, and magnetic fields. As the probes moved through the outer solar system, their instruments recorded the changing conditions of the solar wind. The Plasma Science, or PLS experiment, measured the density, speed, and temperature of charged particles. The low-energy charged particle, or LECP detector, counted ions accelerated by solar events. The Cosmic Ray Subsystem, or CRS, monitored the flux of high-energy particles entering from interstellar space. Meanwhile, the magnetometer, or MAG, mounted on a long boom to avoid interference from the spacecraft's electronics, mapped the strength and orientation of the Sun's magnetic field. Between 1990 and 2000, Voyager 1 crossed from about 47 to 78 AU from the Sunday during this interval. The spacecraft detected fluctuations tied to the Sun's 11-year solar cycle. When the Sun's activity increased, the heliosphere expanded. When it quieted, the bubble contracted. Solar storms, known as coronal mass ejections, blasted plasma outward, creating shock waves that the Voyagers recorded months or even years later. These signals, traveling at hundreds of kilometers per second, allowed scientists to measure how solar energy propagated through the outermost regions of the heliosphere. At the same time, the interplanetary environment grew thinner and colder. By 1993, the solar wind density at Voyager 1's location had dropped to less than 0.001 particles per cubic centimeter, roughly 100,000 times more rarefied than the best laboratory vacuum on Earth. Instruments detected subtle variations in particle velocity and magnetic field direction, providing measurements of how the solar wind slowed under the pressure of the interstellar medium. In 1998, scientists announced that Voyager 1 had entered the heliosheath, where the solar wind slows and its temperature rises due to compression. By that year, the spacecraft was 70 AU from the Sun, about 10.5 billion kilometers, and traveling at 17 kilometers per second. Voyager 2, moving slightly slower at 15 kilometers per second, reached a comparable region a few years later. Magnetometer readings showed chaotic rotations in field direction, indicating interactions between the solar wind and denser interstellar plasma. Maintaining contact with the Voyagers demanded constant ingenuity. The RTGs, which initially produced about 470 watts of power, decayed by roughly 4 watts per year as the plutonium fuel aged. By the late 1990 seconds, available power had dropped below 300 watts. Engineers began cycling instruments, shutting some down temporarily to save energy for others. Heater power was reduced, allowing parts of the spacecraft to operate at temperatures as low as 55 degrees Celsius, beyond original design specifications. Instruments continued functioning despite these conditions. The team at JPL, led by Flight Director Suzanne Dodd and Chief Project Scientist Edward Stone, devised clever methods to preserve operations. Software updates written in machine code were transmitted across billions of kilometers to reconfigure how data was prioritized. Because round-trip communication took nearly 30 hours, commands had to be tested on identical ground-based replicas of the spacecraft before being sent. Every maneuver was executed blindly, with results confirmed days later. By the early 2000s, Voyager 1 had reached 90 AU, nearly 13.5 billion kilometers from the Sunday. The spacecraft's plasma wave instrument detected low-frequency radio emissions, likely generated when shock waves from solar eruptions collided with the interstellar medium. At the same time, the intensity of cosmic rays measured by the CRS instrument began to rise, reflecting reduced deflection by the Sun's magnetic field. In December 2004, Voyager 1 crossed the termination shock, the boundary where the solar wind slows from supersonic to subsonic speeds. The plasma instrument measured an increase in temperature to nearly 250,000 degrees Celsius, although the gas was so tenuous that the heat was imperceptible. Magnetic field sensors recorded sudden compressions and rotations. Voyager 2 followed in August 2007, showing that the termination shock is a wavy surface that expands and contracts with solar activity, varying by up to 10 AU. Beyond the termination shock, the Voyagers traveled through regions of variable charged particle density. The magnetic field intensity rose to about 0.2 nanoteslas, nearly 10 times higher than in the inner heliosphere. Particle detectors measured sporadic bursts of ions accelerated by the shock. Scientists compared these observations to cosmic ray acceleration models to study the production of energetic particles in the galaxy. Each solar cycle altered the conditions of the heliosheath. Between 2009 and 2011, Voyager 1's instruments detected a region where the outward flow of the solar wind nearly vanished a stagnation zone with compressed magnetic fields. Cosmic ray counts doubled as the spacecraft approached the heliopause. During this drift, the Voyagers measured galactic cosmic rays, or GCRs, high-energy particles mostly composed of protons and heavy nuclei, originating from distant supernovae and active galactic nuclei. Voyager's data showed that GCR fluxes increased by roughly 25% per decade as the spacecraft moved outward. As the 2010 seconds began, Voyager 1 was more than 120 AU from the Sunday. The plasma wave instrument, operated by the University of Iowa's Donald Gannett, detected faint oscillations caused by charged particles vibrating in response to solar disturbances. Each oscillation translated into a frequency, which scientists converted into a measurement of electron density, rising from 0.002 to 0.08 electrons per cubic centimeter. The Sun's protective bubble, understanding the heliosphere. Beyond the planetary realm, beyond the orbit of Neptune, lies a region that has long been invisible to human eyes, the heliosphere. It is, in essence, the Sun's protective bubble, a vast envelope of charged particles and magnetic fields carved from the galaxy itself. Voyager's journey through this region provided humanity's first detailed view of the outer limits of the solar system, revealing a complex dynamic frontier where solar energy meets interstellar space. The heliosphere begins where the solar wind, a constant outflow of electrons, protons, and alpha particles dominates the local space environment. Near Earth, this wind flows at roughly 400 kilometers per second, but as it travels outward, it interacts with the Sun's magnetic field and slows due to the pressure from the surrounding interstellar medium. By the time Voyager 1 reached 80 AU in the early 2000s, the solar wind had slowed to velocities around 250-300 kilometers per second. Voyager's plasma detectors recorded regions of compression and rarefaction, indicating variability in the solar wind structure. The Sun's magnetic field, carried outward by the solar wind, twists into a spiral shape due to the Sun's rotation, the Parker spiral, named after physicist Eugene Parker. This spiral creates sectors of alternating magnetic polarity, separated by thin current sheets. Voyager's magnetometer, operated under Edward Smith and later Stamatios Krimagis, recorded these polarity changes over time. Near the heliopause, the field lines were compressed, with magnetic intensities reaching 0.2, 0.3 nanoteslas, 10 times higher than near-Earth orbit. One of the most striking discoveries from Voyager was the termination shock, the first major boundary within the heliosphere. This is where the supersonic solar wind slows abruptly due to interaction with the interstellar medium, creating a shockwave comparable in principle to the sonic boom of a supersonic jet. Voyager 1 crossed the termination shock at approximately 94 AU, while Voyager 2 encountered it at 84 AU, indicating an asymmetry caused by the tilt of the Sun's magnetic axis and the pressure of interstellar material. Measurements from the plasma instruments revealed temperatures of around 250,000 degrees Celsius, far hotter than anything measured within the inner solar system, despite the extremely low particle density of about 0.002 particles per cubic centimeter. These high temperatures indicated that the plasma was being compressed and energized, as it slowed down, a key insight into the dynamics of the outer heliosphere. Beyond the termination shock lies the heliosheath, a high-pressure region where the slowed solar wind accumulates against the interstellar medium. The heliosheath fluctuates in response to solar cycles and galactic forces. Voyager 1's measurements showed magnetic turbulence and energetic particle variations every few days. Particle densities in this region rose to 0.05, 0.08 electrons per cubic centimeter, while plasma temperatures reached hundreds of thousands of degrees. The heliosphere is also a shield against galactic cosmic rays. Voyager's Cosmic Ray Subsystem, or CRS, detected that GCR intensity increases steadily as the spacecraft approaches the heliopause. In the inner heliosphere, the solar magnetic field deflects many high-energy particles, but in the outer heliosheath, cosmic rays penetrate more easily. Voyager 1's data showed that between 2005 and 2012, cosmic ray intensity doubled for particles in the 100-500 MeV range. This rise signaled that the spacecraft was approaching a region where the Sun's protective influence ends and interstellar space dominates. Understanding this interaction is crucial, as cosmic rays pose a significant hazard for future crewed missions beyond the solar system. Voyager observations of the termination shock and heliosheath from both spacecraft indicated that the Sun's magnetic field is not uniform and that the heliosphere is compressed more in the southern hemisphere than in the north. This compression likely results from the local interstellar magnetic field. Models derived from Voyager data suggest the heliosphere is elongated opposite the solar system's motion through the galaxy at roughly 26 kilometers per second. Another intriguing feature identified by Voyager is the so-called ribbon of energetic neutral atoms, or ENAs, which was later confirmed by the Interstellar Boundary Explorer IBEX mission. Voyager's LECP instrument detected fluctuations in energetic particles consistent with this ribbon, a zone where charged particles from the heliosphere interact with neutral atoms from interstellar space. These interactions create a feedback loop, accelerating particles and producing additional heat, an essential factor in explaining the extreme temperatures observed at the heliopause. Magnetic turbulence and plasma compression form the heliospheric wall, observed by Voyager as the region preceding the 50,000-degree plasma wall. In this region, solar wind particles decelerate, accumulate, and are heated by interactions with interstellar gas and magnetic fields. Voyager 1 recorded electron temperatures in the tens of thousands of degrees in the inner heliosheath, with higher ion temperatures. Voyager's plasma wave instrument, or PWS, provided additional insight into the density and temperature of electrons near the heliopause. When solar storms sent shock waves outward, they excited plasma oscillations that the PWS converted into audible signals. By analyzing the frequency of these oscillations, scientists inferred electron densities rising from 0.002 to 0.08 per cubic centimeter, a remarkable method for listening to space. These measurements helped determine the precise location of the heliopause when Voyager 1 crossed it in August 2012 at approximately 121 AU. During the solar maximum of 2000-2001, Voyager instruments recorded a sudden increase in solar wind density and pressure, compressing the heliosheath by nearly 5 AU. Conversely, during solar minima, the heliosphere expanded, allowing interstellar particles to penetrate further inward. Voyager measurements indicated that these expansions and compressions corresponded with changes in solar wind velocity, plasma density, and magnetic field strength across the outer heliosphere. The Voyagers also discovered that the outer heliosphere is filled with anisotropies in particle flux areas where particle density and energy differ depending on direction. These are likely caused by the Sun's magnetic field lines being draped over the heliopause, like threads of a fabric. Some regions act as channels, allowing cosmic rays to funnel into the inner heliosphere, while others deflect particles more effectively. Measurements of these anisotropies were used to refine models of particle transport and magnetic field interactions within the heliosheath, providing detailed input for simulations of solar interstellar boundary dynamics. A critical contribution of Voyager's heliosphere observations was understanding the boundary layer dynamics between the solar and interstellar domains. Unlike planetary atmospheres with clear boundaries, the heliopause is a diffuse, variable frontier where pressure, magnetic field, and particle composition shift continuously. Voyager data indicated that the heliopause thickness could range from 110 AU, depending on solar activity and local interstellar conditions. Continuous measurements of cosmic ray flux, plasma density, and magnetic field strength were recorded over months and years to monitor these variations and their correlation with solar and interstellar conditions. The data also informed astrophysical theories about stellar wind bubbles beyond our solar system. By comparing Voyager's observations to models of other stars' interactions with their galactic environments, scientists can estimate the protective reach of stellar winds and their role in shielding planets from cosmic radiation. Models now incorporate variations in stellar wind pressure, magnetic field strength, and plasma density based on these observations, refining predictions for exoplanetary environments. By the early 2010 seconds, Voyager 1 and Voyager 2 had provided the most detailed map of the heliosphere in history. Voyager 1's crossing of the heliopause at 121 AU confirmed the existence of a sharply heated outer boundary where plasma temperatures approached 50,000 degrees. Voyager 2 would follow 3 years later at 119 AU, allowing a comparative analysis that confirmed the heliosphere is asymmetric, compressed in the south and elongated in the north. The heliosphere extends over 200 billion kilometers and is shaped by the interstellar environment with plasma density, magnetic field strength, and energetic particle flux varying across different regions. Voyager measurements revealed that the outer heliosphere is asymmetric, with the southern hemisphere compressed and the northern hemisphere elongated. Observations also recorded magnetic turbulence, particle flows, and plasma compression that fluctuate with solar activity and local interstellar conditions, providing detailed information on the structure and dynamics of the heliosphere at its boundary with interstellar space. Winds of the sun, the flow that shapes space. At the heart of our solar system lies a star whose influence extends far beyond the orbits of planets, moons, and asteroids. The sun is not a static orb, it is a dynamic engine, constantly expelling a stream of charged particles known as the solar wind. Voyager's journey into the outer solar system allowed humanity to witness, for the first time, the structure and behavior of this solar wind as it travels tens of billions of kilometers away from the sunday. The solar wind originates in the sun's corona, a region of plasma heated to over 1 million degrees Celsius. In this environment, the sun's magnetic field threads the corona like taut strands, and charged particles, primarily electrons, protons, and helium nuclei, are energized enough to escape the sun's gravitational pull. The result is a supersonic outflow that travels outward at speeds ranging from 300 to 800 kilometers per second, depending on solar activity. Voyager's plasma detectors were the first to measure this wind directly at extreme distances, confirming that the solar wind is not uniform, but divided into fast and slow streams that interact in complex ways. In the inner heliosphere, within about 10 AU of the Sun, the solar wind travels relatively undisturbed. The fast wind, reaching up to 750 kilometers per second, originates from coronal holes regions where magnetic field lines are open and particles can escape freely. The slower wind, around 400 kilometers per second, emerges from the edges of active regions and the Sun's equatorial plane. As these streams propagate outward, they begin to interact, creating compression regions known as corrotating interaction regions, or CIRs. Voyager's plasma and energetic particle instruments observed these regions as early as 15 AU, revealing that the solar wind carries the signature of the Sun's rotation all the way into interstellar space. The solar wind carries not only particles, but also the Sun's magnetic field. This magnetic field spirals outward due to the Sun's rotation at a rate of approximately 1 rotation every 25 days at the equator, forming the Parker spiral. Voyager's magnetometer, calibrated and maintained by teams led by Edward Smith and later Stamatios Krimigis, recorded magnetic field strengths declining from 5 nanoteslas at 1 AU to 0.01 nanoteslas beyond 90 AU. The spiral structure creates alternating sectors of magnetic polarity, separated by the heliospheric current sheet, which Voyager observed twisting and undulating with solar activity. This complex magnetic environment guides the solar wind and controls how it interacts with interstellar space. As the solar wind moves outward, it begins to slow due to interactions with the interstellar medium. Around 80-90 AU, Voyager detected the first signs of this deceleration. The supersonic wind encounters the interstellar plasma and magnetic pressure, producing the termination shock. Plasma instruments measured a dramatic increase in temperature to 250,000 degrees Celsius, even though particle density remained extremely low, around 0.00 to 0.003 particles per cubic centimeter. These measurements revealed that energy from the solar wind is transferred into heating the plasma, creating a high-temperature buffer before reaching the heliopause. The solar wind is not only a stream of particles, but a carrier of energy, momentum, and information. Voyager observed periodic fluctuations in wind speed, density, and magnetic field strength, many of which correlated with solar events such as coronal mass ejections or CMEs. CMEs, massive bursts of plasma ejected from the Sun's corona, can reach speeds exceeding 3,000 kilometers per second, traveling across the solar system and compressing regions of the heliosphere like tsunamis in an ocean, Voyager instruments detected these events far beyond the orbit of Pluto, showing that the solar wind transmits disturbances across tens of billions of kilometers, influencing conditions even at the solar system's outermost boundary. Another key discovery was the interaction of the solar wind with charged particles from the interstellar medium. As the solar wind slows in the outer heliosphere, it generates a complex zone where particles are trapped, accelerated, or deflected. Voyager's low-energy charged particle, or LECP instrument, recorded bursts of accelerated particles near 100 AU, which scientists interpreted as evidence of wave-particle interactions in the turbulent Helios heath. Measurements showed that ion energies in this region could reach hundreds of kilo-electron volts, and electron fluxes exhibited rapid fluctuations, providing detailed data on particle acceleration mechanisms in low-density plasma environments. The solar wind also plays a crucial role in shielding the solar system from galactic cosmic rays. Voyager's cosmic ray subsystem showed that within the inner heliosphere, the solar wind's magnetic field deflects a significant portion of high-energy particles from deep space. However, in the outer heliosphere, cosmic rays gradually penetrate as the solar wind weakens. Voyager measurements quantified this gradient, showing that proton fluxes above 100 MeV increased by factors of 2-3 between 80 AU and the heliopause, providing precise data for modeling particle penetration and space weather conditions. Voyager's data further revealed that the solar wind is not isotropic. Fast wind tends to dominate the poles, while slow wind is concentrated near the solar equator. This distribution is influenced by the Sun's magnetic cycle, which reverses approximately every 11 years. During solar maximum, increased solar activity causes the heliospheric current sheet to warp, creating a more turbulent environment. Voyager measurements confirmed that the outer heliosphere is strongly affected by these solar cycles, demonstrating that even at distances of over 100 AU, the Sun's internal processes dictate space conditions. Interestingly, the solar wind also carries a subtle imprint of the Sun's chemical composition. Voyager's instruments detected variations in helium abundance, temperature, and ionization states of hydrogen and helium nuclei. These measurements allowed scientists to track how particles evolve as they propagate outward. For example, the proton-to-alpha particle ratio decreases slightly with distance, reflecting interactions with the interstellar medium and internal heliospheric dynamics. Detailed data from Voyager show that helium abundance varied by up to 10% between 10 AU and 100 AU, and ionization states shifted with solar activity, providing precise parameters for modeling stellar wind transport. Voyager also detected magnetic folds and turbulence in the solar wind, particularly in the outer regions near the termination shock. These fluctuations indicate that the heliospheric magnetic field is not a simple laminar structure, but a chaotic environment where waves, instabilities, and reconnection events continuously redistribute energy. Plasma turbulence in these regions was measured at scales of hundreds of kilometers, small in cosmic terms, but massive for spacecraft-based measurements. Such turbulence contributes to the heating of the Helios sheath and sets the stage for the formation of the 50,000-degree wall observed later. Another remarkable aspect of the solar wind is its role in shaping planetary magnetospheres and atmospheres. While Voyager was beyond planets in the outer solar system, its instruments recorded echoes of past interactions between the solar wind and giant planets. Energetic particle streams observed near Jupiter and Saturn's orbits were later traced to solar wind disturbances, showing that these interactions could accelerate particles to tens of kV and modify local magnetic fields. Even at distances beyond 100 AU, instruments detected lingering particle flux signatures associated with these planetary interactions. Voyager also provided insight into the solar wind's role in the acceleration of energetic neutral atoms. As solar wind ions collide with neutral interstellar atoms, they can transfer energy and become neutral themselves. These ENAs travel in straight lines, providing a remote sensing mechanism to study the heliosphere. Voyager's LECP instrument detected fluctuations in particle fluxes consistent with ENA production, with measured energies ranging from a few keV to tens of keV, confirming continuous interaction between solar wind ions and neutral interstellar matter. Voyager's measurements showed that the solar wind is supersonic near the planets, slows and heats near the termination shock, becomes turbulent in the heliosphere, and finally interfaces with the interstellar medium at the heliopause. Its properties speed, density, temperature, and magnetic structure are shaped by solar activity, interstellar pressure, and interactions of charged particles across billions of kilometers. Voyager data also quantified the plasma temperature rise to 50,000 K near the outer heliosheath. By combining plasma data, magnetic field measurements, cosmic ray detection, and energetic particle analysis, Voyager revealed that the solar wind is a dynamic flow capable of sculpting space and accelerating particles. Voyager's findings quantified its properties across the heliosphere, providing data for modeling stellar winds, magnetospheres, and plasma boundaries around other stars. As Voyager 1 and 2 continued outward, the solar wind's influence waned, but its effects remained visible in the structure, turbulence, and temperature of the plasma. This flow causes compression, heating, and particle acceleration at the boundary regions. Voyager at the termination shock, unveiling the boundary of the solar wind. Voyager 1 and Voyager 2 had traveled billions of kilometers beyond the last planets, their instruments quietly recording the whispers of the sun's fading influence. Beyond the familiar solar wind, a sudden and dramatic transformation awaited: the termination shock. Unlike the serene stretches of plasma that permeated the inner heliosphere, the termination shock represented a violent interface where the solar wind, once supersonic, collided with the rising pressure of interstellar space and was forced to decelerate, compress, and heat. This was the sun's first handshake with the galaxy beyond, and Voyager would witness it firsthand. In December 2004, Voyager 1 crossed this boundary from the Sun, while Voyager 2 followed 3 years later. These two crossings revealed more than just the location of the shock. They exposed an unexpected asymmetry in the heliosphere. Voyager 2's southern path encountered the shock closer to the Sun than Voyager 1's northern trajectory, indicating that the heliosphere was not a perfect sphere, but distorted, likely by the tilt of the Sun's magnetic axis and the interstellar magnetic pressure. The shock's distance was influenced not only by solar wind pressure, but also by interstellar conditions. The environment at the termination shock was unlike anything experienced in the inner solar system. Voyager's plasma detectors recorded sudden jumps in temperature from tens of thousands of degrees to over 250,000 degrees Celsius, despite particle densities remaining extremely low on the order of 0.002 to 0.0003 particles per cubic centimeter. The solar wind, moving at 400–800 kilometers per second just before the shock, abruptly slowed to subsonic speeds, demonstrating a dramatic conversion of kinetic energy into thermal energy. Electrons, protons, and alpha particles were scattered and energized, creating a turbulent region that acted simultaneously as a buffer, a heater, and a particle accelerator. Voyager's low-energy charged particle instrument provided insight into the acceleration of ions at the shock. As the solar wind decelerated, particles were trapped and bounced between turbulent magnetic fields, gaining energy with each reflection. Proton fluxes at energies above 100 keV spiked sharply just beyond the shock, and helium ions experienced similar acceleration. These observations confirmed long-standing predictions that termination shocks could function as natural particle accelerators, providing a localized environment for studying processes responsible for cosmic rays throughout the galaxy. The magnetic field, embedded in the slowing solar wind, also underwent radical transformation. As Voyager 1 approached the shock, its magnetometer recorded the field strength rising from roughly 0.05 nanoteslas in the outer heliosphere to 0.3 nanoteslas. Voyager 2 observed even greater fluctuations, revealing that the Parker spiral, which had twisted gracefully through the inner heliosphere, became distorted, compressed, and folded under opposing interstellar forces. This chaotic configuration created alternating regions of high and low magnetic pressure, producing waves and turbulence that interacted with charged particles, further fueling their acceleration. Researchers noted that these localized magnetic knots were on scales of millions of kilometers, small by cosmic standards, but immense from a spacecraft perspective. Voyager also measured the first clear evidence of the shock's temporal variability. Solar activity, varying over the 11-year solar cycle, sent bursts of faster and denser wind outward. These pulses temporarily shifted the termination shock's location by several AU, a phenomenon directly recorded by Voyager's instruments. In the northern hemisphere, Voyager 1 noted outward excursions of up to 3 AU during peak solar activity, while Voyager 2's southern path contracted under periods of weaker solar wind. The observations confirmed that the termination shock's location fluctuated in response to solar wind variations. Particle-wave interactions played a central role in shaping the shock. Plasma wave instruments aboard Voyager detected oscillations generated by interactions between ions and electromagnetic fluctuations. These waves, ranging from a few hertz to several kilohertz, acted as mediators, transferring energy between ions and electrons and creating the conditions for particle acceleration. By analyzing the wave frequencies, scientists could measure electron densities with extraordinary precision variations as subtle as 0.001 particles per cubic centimeter were detectable. These measurements provided detailed information on the plasma and magnetic field dynamics of the shock. The termination shock also marked the birthplace of anomalous cosmic rays. Neutral atoms drifting from the interstellar medium entered the heliosphere and became ionized, joining the solar wind. Near the shock, these newly ionized particles were accelerated to energies ranging from tens to hundreds of MeV. Voyager's observations verified that this process was highly efficient. Proton fluxes at 100-200 MeV surged by factors of 3 to 5 immediately downstream of the shock, providing quantitative evidence of particle acceleration at the heliospheric boundary. The shock structure was far from uniform. Voyager's dual perspective revealed hemispheric differences. The northern shock encountered by Voyager 1 was elongated and diffuse, while Voyager 2's southern shock was sharper and more compressed. Magnetic turbulence was stronger in the south, while the northern region exhibited higher plasma temperatures. This asymmetry suggested that the heliosphere's shape is influenced both by solar magnetic orientation and by the pressure of the local interstellar medium, producing a highly anisotropic boundary that challenges earlier, simpler models of a symmetrical solar bubble. As the solar wind slowed, Voyager recorded complex layering within the shock. The kinetic energy of the particles was redistributed into thermal motion, waves, and magnetic energy. Ions gained energy more efficiently than electrons, producing temperature differences between species that persisted into the heliosheath beyond. Plasma turbulence, measured in scales of hundreds of kilometers, created irregularities that rippled outward, feeding instabilities and driving small-scale reconnection events. Voyager's plasma instruments revealed additional surprises. small-scale density variations and bursts of energetic particles appeared intermittently across hours and days, highlighting that the termination shock was not a simple discontinuity, but a highly structured and dynamic interface. Voyager 2 recorded particle flux oscillations every 12-14 hours, while Voyager 1 noted variations with slightly longer periodicities. These fluctuations reflected ongoing interactions between solar wind, interstellar plasma, and magnetic fields. The termination shock's influence extended far beyond particle acceleration. It also sculpted the heliosphere into a turbulent, high-pressure environment. Voyager measured plasma densities rising to 0.05, 0.08 electrons per cubic centimeter, and temperatures remaining in the hundreds of thousands of degrees. Magnetic fields in the heliosphere were twisted and contorted, creating pockets of enhanced pressure that could guide charged particles, forming channels and barriers across the outer solar system. These measurements provided evidence of the termination shock's impact on heliosphere structure. By analyzing data from both Voyagers, scientists constructed the first three-dimensional map of the termination shock and its surrounding environment. The shock was revealed as asymmetric, dynamic, and turbulent, its properties shaped by solar activity, magnetic orientation, and galactic pressures. It provided a natural laboratory for observing plasma heating, particle acceleration, wave-particle interactions, and collisionless shock physics on a scale impossible to replicate on Earth. As Voyager crossed the termination shock, instruments recorded the solar system's outermost boundary in detail. The data showed a dynamic, multi-layered region where the supersonic wind slows, heats, and energizes particles, and where magnetic fields twist under interstellar pressures. Observations confirmed the termination shock as a region of extreme conditions, particle acceleration, and complex plasma physics consistent with theoretical predictions. The heliopause, the boundary of two worlds. Beyond the turbulent plasma of the termination shock, a quieter yet profoundly enigmatic region awaited Voyager 1 and 2, the heliopause, the outermost boundary where the Sun's influence finally yielded to the interstellar medium. Unlike the violent deceleration of the termination shock, the heliopause was a subtle yet absolute frontier where the flow of solar wind nearly vanished and the density, composition, and magnetic structure of the surrounding space changed dramatically. It was the line between the familiar solar bubble and the vast, uncharted expanse of the galaxy. For the first time, humanity would measure directly the properties of space beyond the Sun's dominion. Voyager 1 crossed the heliopause on the 25th of August 2012 at a distance of roughly 121 AU from the Sun, while Voyager 2 followed on the 5th of November 2018 at 119 AU. The crossings showed that the heliopause is not a uniform or smooth shell, but a fluctuating, asymmetric interface, shaped by the solar magnetic field, local interstellar pressure, and the direction of the interstellar magnetic field. Voyager's plasma, cosmic ray, and magnetometer instruments captured a sudden shift. Solar wind density dropped from 0.00 to 0.003 electrons per cubic centimeter to near zero levels, while interstellar plasma density measured roughly 0.08 electrons per cubic centimeter. Magnetic measurements across the heliopause revealed a remarkable phenomenon. The Sun's magnetic field, which had dominated the inner heliosphere and the heliosheath, twisted and folded as it approached the boundary. Voyager 1 recorded a sudden reorientation in field direction by nearly 30 degrees as it entered interstellar space, while field strength stabilized around 0.1, 0.2 nanoteslas higher than expected in the heliosheath, suggesting compression and tension at the boundary. Voyager 2 noted similar directional shifts, confirming that the heliopause is a highly magnetized, anisotropic interface, where solar and interstellar magnetic fields interact, sometimes forming small-scale reconnection events capable of accelerating particles. Cosmic rays provided measurable evidence of the heliopore's effect on particle flux. Inside the heliosphere, the Sun's magnetic field and solar wind partially deflect high-energy galactic cosmic rays, producing a gradient in particle flux. As Voyager crossed the heliopause, proton and helium fluxes above 100 MeV surged by factors of 3.5, while low-energy solar particles sharply decreased. Voyager's cosmic ray subsystem confirmed that the heliopause separates regions dominated by solar wind particles from those dominated by galactic cosmic rays. These measurements quantified the shielding effect of the Sun across hundreds of AU. The heliopause was also a site of wave activity and turbulence. Voyager's plasma wave instrument detected broadband plasma oscillations with frequencies between 1 and 10 kHz, indicative of interactions between the sparse interstellar plasma and residual solar wind flow. Electron densities inferred from these waves suggested that the boundary is permeable on small scales, allowing some solar origin particles to leak outward while interstellar ions occasionally penetrate inward. These measurements indicate a complex interface where energy, particles, and magnetic tension interact across small and large scales. One of the most notable discoveries was the asymmetry of the heliopause. Voyager 1, traveling through the northern hemisphere of the heliosphere, encountered the boundary farther from the Sun than Voyager 2 inches the south. Scientists attributed this to the tilt of the interstellar magnetic field, which presses more strongly on the southern hemisphere, compressing the heliopause inward. Variations in solar wind pressure over the solar cycle caused the boundary to shift by several AU over decades, indicating its dynamic behavior. In the outer heliosphere, Voyager instruments observed plasma flows that were not uniform. As the spacecraft approached the heliopause, solar wind speed dropped below 100 km per second, sometimes oscillating between outward and slightly inward motion, creating a phenomenon scientists called boundary turbulence. These fluctuations were tied to magnetic instabilities and pressure gradients at the heliopause. Voyager's measurements showed that ions in this region could reach temperatures of tens of thousands of degrees, while electron temperatures remained slightly lower, creating a partially stratified plasma environment. This stratification provided new clues about the transfer of energy between particles and fields in a low-density, high-energy environment. Energetic neutral atoms offered another way to study heliopause dynamics. When solar wind ions collided with interstellar neutrals, they became neutral themselves and traveled in straight lines, carrying information about the interface back to Voyager. The spacecraft detected ENAs with energies from a few kV up to tens of kV, mapping regions of high solar wind, interstellar interaction, and confirming structures later visualized by NASA's IBEX mission. These data demonstrated that the heliopause produces measurable fluxes of energetic neutral atoms originating from both solar and interstellar interactions. Voyager's magnetometer also recorded fine-scale folds and ripples in the heliopause's magnetic field, sometimes referred to as magnetic wrinkles. These structures, tens of thousands of kilometers across, acted as localized channels and barriers for charged particles. Protons and electrons were observed to gyrate along these folds, temporarily trapped before either returning to the heliosheath or entering interstellar space. This behavior confirmed that the heliopause is a complex, three-dimensional surface where magnetic topology dominates particle motion, creating pockets of enhanced pressure and localized turbulence. In addition to its structural complexity, the heliopause marked a compositional transition. Voyager detected a change in plasma composition, with helium to proton ratios slightly higher in the interstellar medium than in the solar wind. Ionization states also differed. While solar wind protons were mostly singly ionized, Interstellar hydrogen contained a higher fraction of neutral atoms, reflecting the pristine conditions of space beyond the Sun's influence. These data provided critical constraints for models of particle transport, filtration of interstellar neutrals, and the evolution of cosmic plasma at the interface between a star and its galactic environment. Voyager also observed particle acceleration near the heliopause, particularly of anomalous cosmic rays. These particles, originating from neutral interstellar atoms that were ionized and entrained in the solar wind, gained energy in the outer heliosheath and at the boundary itself. Proton energies reached several hundred MeV, while heavier ions, like helium and oxygen, achieved tens of MeV per nucleon. The spacecraft confirmed that acceleration processes at the heliopause can increase ion energies to hundreds of MeV. Temperature gradients across the heliopause revealed another layer of complexity. While plasma in the heliosheath averaged tens of thousands of degrees, interstellar plasma measured by Voyager stabilized near 10,000–15,000 degrees, showing a sharp thermal boundary. Yet turbulence and wave-particle interactions smoothed some transitions over millions of kilometers, creating a mixed zone where particle populations partially overlapped. These measurements helped refine models of heat and energy exchange at stellar boundaries. The heliopause also provided insight into the solar system's orientation in the local interstellar medium. Voyager data revealed that interstellar plasma flowed past the solar bubble at approximately 26 kilometers per second relative to the Sun, while interstellar magnetic field lines were inclined roughly 60 degrees from the solar equatorial plane. These measurements confirmed that the heliosphere is shaped not only by the solar wind, but also by the direction and pressure of interstellar gas and magnetic fields, creating a comet-like asymmetry with a long tail extending opposite the Sun's motion. Voyager confirmed that the heliopause is a transitional region rather than an impenetrable barrier. While the solar wind effectively ends at the boundary, small fractions of particles and magnetic flux can leak across, creating interactions on both sides. These interactions generate instabilities, microturbulence, and wave activity that propagate into interstellar space. Voyager's instruments captured these effects in detail, providing direct measurements of the physical processes occurring at the boundary between the heliosphere and interstellar space. Deep Space Network, keeping Voyager's voice alive. Beyond the heliopause, Voyager 1 and Voyager 2 continue to transmit signals to Earth. Their radio emissions are extremely faint, a narrow-band stream of energy spreading across billions of kilometers of space. Each bit of data that reaches Earth, from magnetic field readings to plasma wave measurements, originates from a transmitter built nearly half a century ago. Voyager's ability to communicate across unprecedented distances represents one of the longest-range data links ever maintained. By 2025, Voyager 1 is more than 24 billion kilometers from Earth, about 160 astronomical units. Its 23-watt transmitter, comparable in power to a small light bulb, sends a signal that weakens to less than a 10 billionth of a trillionth of a watt by the time it reaches Earth. Detecting that signal requires NASA's Deep Space Network, among the most sensitive radio receivers ever constructed. The Deep Space Network consists of 3 facilities positioned so that at least one can observe any point in the sky as Earth rotates: Goldstone, California, near Madrid, Spain, and near Canberra, Australia. Each site houses antennas, the largest being 70 meters across, capable of detecting signals far weaker than the background noise of the universe. The faint pulses from Voyager take more than 22 hours to reach Earth, where they are received by the DSN dishes, converted into electric currents, and decoded into numerical data. When the Voyagers launched in 1977, the DSN was designed for planetary missions, Mars orbiters, lunar probes, and interplanetary craft operating within a few dozen astronomical units. As Voyager continued outward, engineers upgraded the DSN to handle greater distances. Over the decades, the receivers were fitted with ultra-low noise amplifiers cooled by liquid helium, increasing sensitivity tenfold. Software-defined demodulators replaced analog hardware, enabling detection of Voyager's narrowband 8.4 GHz carrier frequency within background radio noise. Commands are sent to Voyager on an uplink frequency of 2.1 GHz. At a distance of 24 billion kilometers, round-trip light time is about 44 hours. When engineers at NASA's Jet Propulsion Laboratory transmit software sequences, sometimes only a few kilobytes, they are encoded, verified, and sent by the 34 or 70-meter antennas using kilowatt-level power. The spacecraft's receiver, roughly the size of a small box, continuously monitors this channel, distinguishing incoming commands from background radio noise. Voyager's data transmission system relies on ancient but remarkably reliable technology, the Traveling Wave Tube Amplifier, or TWTA. The TWTA boosts the spacecraft's 23 watts of power through a narrow antenna beam, only 3 degrees wide. The high-gain antenna, a 3.7-meter parabolic dish, must be pointed toward Earth with an accuracy of less than 1/10 of a degree. Any drift means the signal vanishes into space. Because the spacecraft tumbles slightly due to minute thruster leaks and thermal stresses, engineers constantly recalculate and adjust its attitude, sending correction commands to the tiny hydrazine thrusters that still respond after nearly 5 decades. The information Voyager transmits is digital but limited in rate, about 160 bits per second for science data and 40 bits per second when power is low. For comparison, a modern smartphone transmits millions of bits per second. The telemetry packets include magnetometer readings, cosmic ray counts, plasma wave frequencies, and engineering data such as temperature, voltage, and power output from each of the spacecraft's 3 radioisotope thermoelectric generators. Each RTG now produces about 160 watts, down from 470 watts at launch, and that reduction limits data transmission. To conserve energy, engineers sequence the instruments to operate one at a time. When the plasma wave instrument listens for oscillations, the magnetometer sleeps. When the cosmic ray subsystem counts high-energy particles, the ultraviolet spectrometer is powered down. The data are stored on a digital tape recorder with only 68 kilobytes of memory, smaller than a single modern digital photograph, before being transmitted in slow bursts during the DSN's scheduled contact windows. At JPL, in a control room lined with monitors and signal analyzers, the flight operations team monitors the spacecraft's heartbeat, a carrier tone. When that faint frequency shifts even by a few millihertz, it tells them something about the spacecraft's motion or condition. A Doppler shift of 1 Hz can reveal that the probe's velocity has changed by fractions of a millimeter per second. Using these tiny variations, engineers have measured the gravitational pull of the Sun, the planets, and even the subtle pressure of sunlight across decades. The resulting Doppler tracking data have been used to test general relativity and refine the mass distribution of the outer solar system with extraordinary precision. As Voyager entered interstellar space, its communication environment changed significantly. The heliosheath and heliopause acted like refractive layers, scattering and bending radio signals. Between 2013 and 2016, Voyager 1's signal fluctuated due to plasma density variations beyond the heliopause, which caused measurable time delays in transmission. From these distortions, scientists estimated the electron density of interstellar space at about 0.05 electrons per cubic centimeter, data inferred from changes in the spacecraft's radio signal behavior. The DSN maintains communication through a global relay system. When Goldstone loses sight of Voyager 1, the Madrid station takes over, followed by Canberra approximately 12 hours later. To detect the faintest signals, multiple stations can operate simultaneously. In 2020, for example, the 70-meter dish in Canberra was electronically linked with the 100-meter Green Bank telescope in West Virginia to increase sensitivity. This technique, called Very Long Baseline Interferometry, allows Earth-based antennas to function as a combined, high-resolution receiving system. Upgrades to the DSN over time have allowed Voyager to keep talking far longer than its designers thought possible. In 1977, mission planners predicted communication might last until the late 1990 seconds. But with improved signal processing, even data streams at the threshold of detectability can be recovered. Modern digital filters can extract a signal just a few decibels above the cosmic background. Software at JPL reconstructs corrupted bits by cross-checking redundant packets, a process that can take days for a single transmission session. In 2021, Voyager 1's plasma wave subsystem detected a persistent, low-frequency signal from interstellar space, a continuous tone near 3 kHz, indicating a steady background plasma density. These waves differed from the short bursts associated with solar shocks. The measurements showed that the interstellar medium beyond the heliopause maintains a stable electron density and low-level plasma oscillations. The signal that carried this data to Earth had a received power of approximately 10 to the power of -20 watts, far below any terrestrial transmission level. Communication with such ancient machines demands meticulous discipline. The DSN schedule allocates only a few hours each week for each Voyager, as newer missions Mars orbiters, the James Webb Space Telescope, and the Artemis lunar program also rely on the network. Before each session, engineers model the spacecraft's expected location to within a few thousand kilometers, accounting for gravitational perturbations, the sun's radiation pressure, and even thermal recoil from the RTGs. Commands are then sent in carefully timed sequences, often consisting of only a few dozen instructions. Some are routine, reorienting the antenna, adjusting data rates, switching power modes, but others rewrite memory registers that have been active since the 1972nd. Over the decades, Voyager operations have encountered technical challenges. In 2010, Voyager 2's computer entered safe mode after a corrupted data word changed its telemetry format. Engineers traced the problem to a single bit error in onboard memory and transmitted a 1-byte corrective patch approximately 14 billion kilometers to the spacecraft. The procedure restored normal operations and represented one of the farthest remote software corrections performed in spaceflight. Temperature fluctuations create additional challenges. With heaters shut down to conserve power, some components operate below 50 degrees Celsius. The radio transmitter, originally designed for room temperature operation, must remain frequency stable despite these extremes. Engineers continuously monitor oscillator drift, as deviations of only a few parts per trillion can affect communication. Modeling of thermal contraction in the antenna and precise attitude control has maintained the beam alignment with Earth for nearly 5 decades. Today, Voyager data continue to pass through NASA's Spaceflight Operations Facility in Pasadena, California. A team of engineers interprets the transmissions using original documentation from the 1970 seconds and software written in Fortran 77 to decode the spacecraft's telemetry. The team maintains operational expertise as the mission continues to function on aging hardware. Each data packet transmitted by the Voyagers contributes to a time series extending nearly 50 years, forming the longest continuous record of solar and interstellar interaction. The spacecraft's radio waves, as they pass through varying plasma densities, provide information about the structure and turbulence of interstellar space. The discovery of the 50,000-degree wall, When Voyager 1 crossed the heliopause in August 2012, engineers at NASA's Jet Propulsion Laboratory didn't immediately realize what had happened. The spacecraft was nearly 8 billion kilometers from the Sun, so far that radio commands took more than 17 hours to reach it. To those monitoring its stream of numbers, the data looked strange but not definitive. Cosmic ray counts were rising, magnetic fields were intensifying, and plasma waves were singing through the instruments like faint radio static. Then, on the 9th of April 2013, a sudden spike appeared in the plasma wave instrument. The frequency of those waves corresponded to a dense region of ionized gas, far denser than anything inside the heliosphere. That was the moment humanity first confirmed. Voyager 1 had entered a new domain. The unexpected finding was the high plasma temperature beyond the heliopause. Instrument readings indicated electron temperatures near 50,000 degrees Celsius, suggesting that the boundary region contained shock-heated plasma rather than the cooler interstellar gas that earlier models predicted. Scientists described this as an interstellar boundary layer, a zone of compressed, heated plasma between the heliosphere and the surrounding interstellar medium. The plasma wave instrument, developed at the University of Iowa under Donald Gannett and later William Kurth, had been one of Voyager's most resilient tools. Even after 35 years in space, its sensors were sensitive enough to detect faint vibrations in the surrounding plasma. Each burst of plasma oscillation translated into an electron density reading. Inside the heliosphere, Voyager had typically measured about 0.002 electrons per cubic centimeter. But now, it was detecting densities exceeding 0.08 electrons per cubic centimeter, 40 times higher proof that it was outside the Sun's protective bubble. In the following months, the magnetometer readings confirmed a major transition. The direction of the magnetic field shifted only slightly, but its strength increased to 0.5 nanoteslas, an intensity consistent with compression. This meant Voyager was in a zone where solar and interstellar magnetic fields were colliding head-on, squeezing the plasma between them like a pressurized cushion. The data matched predictions made decades earlier by astrophysicists Meravofa and John Richardson, who had modeled the heliopause as a magnetized sheath capable of heating to tens of thousands of degrees through shock and compression. By 2014, researchers from NASA, Caltech, and the University of Maryland referred to this feature as the plasma wall. It was not a solid structure, but a region several astronomical units thick, where interstellar ions and solar particles interacted turbulently. Voyager recorded brief electron plasma oscillations lasting seconds, consistent with shock-driven turbulence. The inferred temperature averaged is approximately equal to 50,000 K, varying with plasma density. To understand this environment, scientists analyzed 16 months of continuous data transmitted from Voyager's cosmic ray subsystem and low-energy charged particle instruments. The CRS, managed by Norman Ness and later Stamatios Krimagis, recorded a rapid surge in galactic cosmic rays, an increase of 9% over 30 days, while the LECP registered sharp declines in lower-energy solar particles. The crossover point, where outward-moving solar particles dropped and incoming cosmic rays rose, marked the boundary of influence. Voyager had passed from a solar-dominated region into one governed by the galaxy. At the same time, plasma measurements suggested that the wall was far from uniform. Instead, it appeared layered, alternating bands of higher and lower density, possibly created by years of solar wind variability. Each solar cycle sends waves of energy outward. When they collide with the interstellar medium, they form ripples, heating the plasma and creating pockets of higher temperature. Voyager 1's data indicated at least 3 distinct layers of plasma density during its initial crossing. To corroborate these findings, NASA turned to another spacecraft, the Interstellar Boundary Explorer, orbiting Earth since 2008. IBEX detects energetic neutral atoms particles, born when charged solar wind ions exchange electrons with interstellar atoms. These ENAs trace interactions at the heliosphere's edge. IBEX's observations in 2013 revealed a band of enhanced ENA flux, the so-called IBEX ribbon, located in the same direction as Voyager's trajectory. The ribbon's intensity matched the plasma densities Voyager detected, suggesting both were observing the same phenomenon from different vantage points. The temperature of 50,000 degrees puzzled scientists at first. In such an environment, atoms are almost entirely ionized, yet the particle density is so low, mere fractions per cubic centimeter, that it would feel colder than the vacuum of a laboratory chamber. The heat here refers to the energy per particle, not physical warmth. As Voyager crossed deeper, particle detectors showed evidence of suprathermal ions, charged particles accelerated by magnetic reconnection between solar and interstellar fields. These interactions released bursts of energy equivalent to billions of joules per cubic kilometer, enough to heat particles to tens of thousands of degrees, without creating visible light or radiation harmful to the spacecraft. Additional evidence came from solar outbursts in 2014 and 2017. Coronal mass ejections, observed by SOHO, took more than a year to reach the heliopause. When they did, Voyager's plasma wave instrument recorded strong oscillating emissions. Timing these events indicated that the shock fronts traveled at about 400 kilometers per second. The resulting temporary increases in plasma density and temperature confirmed that solar activity can affect conditions even at distances near 20 billion kilometers. What astonished researchers most was the stability of Voyager's instruments amid these extremes. The spacecraft's RTGs, producing just 250 watts of power, continued to feed the plasma, magnetometer, and cosmic ray systems. Engineers at JPL, led by Suzanne Dodd and Jefferson Hall, reprogrammed data transmission sequences to prioritize the most critical science readings. Each bit of information, less than 160 bits per second, took over 18 hours to reach Earth. Yet from these faint signals, entire maps of the outer heliosphere were constructed. In 2018, Voyager 2 confirmed the existence of the plasma wall from a completely different angle. Crossing the heliopause at 119 AU, in the southern hemisphere of the heliosphere, it detected nearly identical plasma densities and temperatures. However, it recorded slightly higher magnetic turbulence, suggesting that the Sun's motion through the local interstellar medium compresses the southern side of the heliosphere more strongly. The comparison between the two spacecraft, separated by nearly 67 degrees in heliographic latitude, allowed researchers to triangulate the shape and thickness of the wall. It appeared to extend 10-15 AU in thickness, roughly 1.5 billion kilometers, before transitioning into undisturbed interstellar plasma. The measurements required updates to existing heliospheric models. Earlier simulations predicted temperatures of about 10,000 K in the outer heliosheath, but Voyager data showed plasma near 50,000 K. Researchers proposed explanations including intermittent magnetic reconnection between solar and interstellar fields and compression shocks generated by overlapping solar cycle pressure waves. Additional insights came from Voyager's cosmic ray data. The flux of high-energy particles above 100 MeV increased by nearly 30% after crossing the wall. This indicated that the heliosphere shields only part of the cosmic radiation from deep space. As Voyager moved further, it detected an interstellar environment where particle densities stabilized at 0.09 electrons per cubic centimeter and magnetic fields aligned with the galactic plane. The spacecraft had finally entered the Milky Way's unfiltered plasma environment. At NASA's Spaceflight Operations Facility, analysts including Linda Spilker, William Kurth, and Stamatios Krimigis reviewed the data, confirming the existence of a compressed plasma region. The combined increases in plasma wave frequency, magnetic field intensity, and cosmic ray flux matched theoretical expectations for a heated boundary layer. The term plasma wall was adopted in technical discussions to describe this region that limits the outward flow of solar particles. Plasma fire. What a 50,000 degree temperature means in space. Temperature is a familiar word on Earth, but in space it becomes something alien, something that defies the senses. When scientists say the region beyond the heliopause burns at 50,000 degrees, it doesn't mean a spacecraft like Voyager is melting. In fact, if a human could somehow stand there, they would freeze almost instantly. The paradox of hot and cold in the vacuum of space reveals how differently heat behaves where matter is almost absent. Temperature, in physics, is not about warmth, but about motion, the average kinetic energy of particles. In air, there are about 25 quintillion molecules in every cubic centimeter, constantly colliding, sharing energy, and producing the sensation we interpret as heat. But in interstellar space, there are fewer than one particle per cubic centimeter. Each of those particles might be moving at hundreds of kilometers per second, carrying immense energy individually, but because there are so few collisions, they can't transfer that energy effectively. The result is a plasma that is technically hot, but functionally cold. Voyager's instruments did not measure temperature directly. Instead, they detected oscillations in the plasma wave instrument. These oscillations had frequencies corresponding to electron densities between 0.05 and 0.09 per cubic centimeter, which, when converted using plasma physics equations, implied temperatures between 40,000 and 60,000 kelvins. Each oscillation represents the vibration of electrons moving through space, providing a quantitative measurement of plasma conditions. The heating mechanism itself is still debated. One major explanation is adiabatic compression. As the solar wind slows and piles up against the interstellar medium, its energy converts into thermal motion. When Voyager 1 crossed this region, the plasma speed dropped from 400 kilometers per second to less than 100 kilometers per second, while density increased nearly 40-fold. By the conservation of energy, that kinetic loss must reappear as heat, raising the temperature to tens of thousands of degrees. But this isn't the whole story. The magnetic data suggested something even more violent: magnetic reconnection, a process where tangled magnetic field lines snap and reform, releasing energy explosively. Magnetic reconnection is familiar. Closer to home, it drives solar flares and auroras on Earth. At the heliopause, the fields involved are weaker, around 0.4 to 0.6 nanoteslas, and their collisions occur over distances measured in astronomical units rather than kilometers. When Voyager's magnetometer detected sudden fluctuations in field direction in 2013 and 2015, researchers determined these were likely sites of reconnection events heating localized regions of plasma. Models from NASA's Goddard Space Flight Center estimated that such events could inject 10-21 joules of energy into a cubic astronomical unit of space, roughly the same energy Earth receives from the Sun in a day. Another piece of the puzzle came from energetic particle data. Voyager's low-energy charged particle instrument recorded short, irregular bursts of protons and electrons at energies between 30 and 100 Kelvin signatures of shock acceleration. These bursts were temporally linked to the arrival of solar transients, such as coronal mass ejections, suggesting that waves traveling outward from the Sun were still energizing the plasma at the boundary. When these waves collided with the interstellar plasma, they created turbulence eddies of charged particles whipping through magnetic fields at near relativistic speeds. That turbulence, scientists concluded, was the real source of the heating. At Caltech, space physicist Ed Stone, the mission's chief scientist since its launch in 1977, reported that particle motion in the region followed a power law energy distribution typical of turbulence-driven acceleration, rather than the smooth Maxwellian distribution of thermalized gases. This meant the plasma was not uniformly heated. Some ions gained high velocities, while others remained nearly stationary. Voyager's observations were later compared with data from the Interstellar Boundary Explorer and its successor, IMAP, or Interstellar Mapping and Acceleration Probe, launched in 2025. IBEX's measurements of energetic neutral atoms showed regions of high-energy emission consistent with plasma at tens of thousands of degrees, consistent with Voyager's measurements. IMAP's early data, transmitted from Earth orbit, revealed a similar temperature gradient at the edge of the heliosphere. To understand this environment, it can be compared with other cosmic plasmas. The solar corona reaches temperatures above 1 million K, but its density is about 10^8 particles per cubic centimeter, billions of times denser than the plasma around Voyager. The interstellar medium beyond the heliopause has temperatures near 7,000 K and densities of 0.05 atoms per cubic centimeter. The plasma at the 50,000 degree wall has intermediate temperature and extremely low density compared with these environments. The plasma composition adds further complexity. Data from Voyager's plasma science system indicated that protons made up about 96% of the charged particles, with alpha particles at around 4%, and trace amounts of heavy ions like oxygen and carbon. The charge states of these particles suggested partial recombination. Some electrons had reattached to ions, forming quasi-neutral atoms that could travel vast distances unimpeded. These interactions correspond to the energetic neutral atoms observed by IBEX and IMAP and contribute to changes in the ionization balance between the solar wind and interstellar gas. In 2020, a study led by astrophysicist Jamie Rankin at Princeton University used Voyager's data to model the dynamics of the wall. The team found that the temperature spike to 50,000 K likely extends over a region 15 AU thick, with steep gradients in both density and pressure. Their simulations indicated that the plasma behaves like a shock sheath, where incoming solar material decelerates and disperses energy through magnetohydrodynamic waves. The structure resembles a bow shock in fluid dynamics, with a deceleration region forming ahead of the moving solar wind. Understanding this plasma environment provides data for modeling other stars. Observations from the Hubble Space Telescope and the European Space Agency's Gaia mission have detected bow shocks around dozens of nearby stellar systems. Many of these show thermal signatures consistent with temperatures between 30,000 and 70,000 K, comparable to the temperatures observed by Voyager. Despite the high plasma temperatures, Voyager continues to function normally because the density is extremely low, billions of times thinner than air at sea level. The spacecraft experiences negligible friction or heating. Its aluminum body remains near 60 degrees Celsius, warmed only by the 250 watts of its plutonium-powered generators. The discovery of the plasma wall provides information about cosmic shielding. Within the heliosphere, the solar wind's magnetic field deflects most galactic cosmic rays, but in the wall, that protection decreases. Data from Voyager's cosmic ray subsystem showed an abrupt 25% rise in high-energy cosmic particles within weeks of crossing the heliopause. These particles, some exceeding 1 GeV, originate from supernova remnants and distant galaxies, providing direct measurements of the interstellar particle environment. Engineers studying spacecraft shielding use Voyager's data to design systems capable of surviving prolonged exposure to high-energy radiation and temperature gradients in deep space. Observations indicate that any probe traveling beyond the heliosphere must withstand fluxes of 300 particles per square centimeter per second at energies above 100 MeV conditions, far harsher than near-Earth space. By 2025, researchers will continue to monitor Voyager's slow passage through this heated boundary. The physics of a cosmic shockwave. The universe is filled with shockwaves, vast and invisible, rippling through space like unseen tsunamis. At the edge of our solar system, Voyager encountered one of the most dramatic examples, the termination shock. Unlike planetary bow shocks or the more familiar shockwaves in Earth's atmosphere, the termination shock is enormous, stretching over billions of kilometers and unique, because it exists in a medium nearly a vacuum. When Voyager 1 crossed the termination shock, it recorded an immediate deceleration of the solar wind from roughly 400 kilometers per second to subsonic speeds near 150 kilometers per second. Voyager 2 encountered the same boundary in August 2007 at 84 AU, revealing an unexpected asymmetry in the heliosphere's shape. This discrepancy is attributed to a tilt in the Sun's magnetic axis and pressure from the interstellar magnetic field, which compresses the southern hemisphere more than the north. Plasma instruments on board both spacecraft recorded particle densities of about 0.00 to 0.003 electrons per cubic centimeter, confirming that despite the vast distances, the plasma is highly energetic. Temperature readings were measured by Voyager 1's plasma instrument, showing proton temperatures reaching roughly 250,000 degrees Celsius, with extremely low particle density. Heating was observed to be non-uniform, with localized hot spots appearing where interactions between the solar wind and interstellar medium intensified plasma compression. These measurements provided data relevant to theories of collisionless shocks, where particles gain energy via electromagnetic forces and wave-particle interactions rather than through collisions. Magnetic field data revealed another layer of complexity. The Parker spiral, twisted by the Sun's rotation, becomes increasingly distorted at the shock. Voyager's magnetometer recorded sudden intensifications, with field strengths rising from 0.1 to 0.2 nanoteslas, while polarity sectors compressed and folded in unexpected patterns. Scientists observed that these folds create turbulence, which channels energy into heating ions and accelerating electrons. The turbulence also generates localized shock fronts, producing miniature, nested shock waves within the broader termination shock. Edward Smith and Stamatios Krimigis, who led the magnetometer team, noted that these fluctuations could persist for weeks, reflecting the dynamic nature of this boundary region. Voyager's low-energy charge particle, or LECP instrument, recorded ions near the termination shock reaching energies of 110 kilo-electron-volts. Voyager 2 detected ions in the 0.88 keV range. The data show that solar wind ions gain energy by bouncing between magnetic field fluctuations in a process called diffusive shock acceleration, contributing to the population of anomalous cosmic rays observed in the heliosheath and beyond the heliopause. Voyager recorded density structures at the termination shock, with plasma densities fluctuating between 0.0015 and 0.0035 electrons per cubic centimeter, over spatial scales of millions of kilometers. These structures correspond to regions where the solar wind's fast and slow streams interact prior to the shock, creating shock ripples and foreshocks analogous to those observed ahead of planetary bow shocks. The foreshocks produce waves and turbulence that propagate downstream into the heliosheath. One of the most fascinating observations was the generation of energetic neutral atoms near the shock. As solar wind ions collide with neutral interstellar atoms, some are converted into fast-moving neutrals, which Voyager's instruments indirectly detected via changes in ion fluxes. These ENAs travel in straight lines, escaping the magnetic confinement of the solar wind, providing scientists with a remote sensing tool for mapping the shock structure. The discovery of this ENA production confirmed predictions made by the Interstellar Boundary Explorer mission, linking Voyager's in-situ measurements to global heliospheric phenomena. Temperature anisotropies were observed, with electrons at roughly 60,000 degrees Celsius and ions over 250,000 degrees. Electrons respond faster to electromagnetic fluctuations, while heavier ions absorb energy more slowly, creating a 2 temperature plasma environment. These conditions provide data for studies of energy partitioning in low-density, high-energy plasmas. Voyager's cosmic ray subsystem recorded that lower-energy galactic cosmic rays are partially deflected at the termination shock, while higher-energy particles penetrate more easily into the heliosphere. The flux of 100-500 MeV protons increased by approximately 30–40% after crossing the shock. Another striking feature was the spatial variability of the shock. Voyager 1's crossing at 94 AU showed a broad, gently sloping transition, whereas Voyager 2's crossing at 84 AU was sharper, more abrupt, and accompanied by higher local turbulence. Researchers such as Merav Ofer and Nathan Schwadron have used these observations to refine three-dimensional magnetohydrodynamic models of the heliosphere. Voyager's plasma wave instrument captured additional phenomena. As the shock propagated through irregular plasma regions, it excited oscillations in electron density at frequencies of 2–5 kHz. Analysis of these waves revealed fine structures corresponding to localized density enhancements of 10–20%. The termination shock moves outward or inward over solar cycles. During the 11-year solar maximum, the shock can be compressed by 3–5 AU due to increased solar wind pressure, while during solar minimum, it can expand, altering the region where particle acceleration occurs. The termination shock transitions into the heliosheath, the turbulent region beyond. The energy transferred to particles feeds turbulence downstream, heating plasma to tens of thousands of degrees and accelerating particles further. Voyager's measurements of ion distributions, wave turbulence, and magnetic fluctuations were collected. Comparable shock waves are thought to exist around other stars, pulsar wind nebulae, and supernova remnants. Voyager quantified the shock's location, structure, and dynamics, and recorded its particle acceleration capabilities. Data on variations in density, temperature, and magnetic fields were collected for modeling the heliosphere and planning spacecraft operations in interstellar space. Magnetic barriers and the hidden structure of the edge. Beyond the termination shock lies a turbulent, complex frontier, the heliosheath. Here, the sun's influence continues, but the environment is dominated by interactions between the solar wind, magnetic fields, and incoming interstellar matter. Voyager's instruments revealed that this boundary region is far from simple. Instead, it is a labyrinth of magnetic barriers, turbulence, and particle acceleration zones, which collectively define the outermost structure of the heliosphere. One of the most striking discoveries was the presence of magnetic folds and ridges, invisible yet detectable through Voyager's magnetometer readings. Edward Smith's team observed that the field strength fluctuated between 0.05 and 0.15 nanoteslars across regions spanning tens of millions of kilometers. These folds indicate that the heliospheric magnetic field is not a smooth spiral, but a highly twisted and distorted network. Stamatios Krimigis noted that these distortions arise from the combined effects of solar rotation, variations in solar wind speed, and pressure from the interstellar magnetic field. Voyager data showed that some folds rotate on scales of weeks, while others persist for months, creating a dynamic, ever-changing magnetic landscape. Embedded within these folds are what scientists describe as magnetic barriers. These barriers, formed where magnetic field lines converge and compress, act as temporary walls, slowing the flow of charged particles and redirecting their paths. Voyager 1 detected fluctuations in particle flux as these barriers passed over the spacecraft, with ion energies ranging from 10 to 100 keV. Voyager 2, encountering the heliosheath at a slightly closer distance, observed comparable energy ranges but noted more pronounced variations in density, suggesting that the heliosheath is asymmetric, shaped by interstellar pressure differences and the orientation of the galactic magnetic field. Voyager's plasma wave instruments revealed that these magnetic structures generate turbulence at multiple scales. Waves with frequencies between 1 and 5 kHz were detected, corresponding to density oscillations of 5–15%. Smaller, higher frequency fluctuations in the 10–50 kHz range indicated the presence of microinstabilities, likely driven by particle reflections from the magnetic barriers. Such turbulence is critical for the heating of the plasma. Voyager's plasma instrument recorded temperatures rising from 50,000 degrees in the inner heliosheath to approximately 70,000–80,000 degrees in more compressed regions, confirming that magnetic turbulence redistributes energy and sustains high temperatures over enormous distances. Another key discovery was the patchy distribution of energetic particles. Voyager's LECP instrument detected bursts of ions and electrons with energies up to 200 keV, concentrated near regions where magnetic barriers intersected or folded over. These energetic particle pockets often coincided with magnetic ridges, suggesting that the field structures themselves act as particle accelerators. The process is similar to shock acceleration, but rather than a single shock front, the acceleration occurs through repeated interactions with multiple small-scale magnetic obstacles. This mechanism contributes to the population of anomalous cosmic rays, which eventually leak out into interstellar space. Voyager's magnetometer also recorded evidence of what scientists call magnetic reconnection. This process occurs when magnetic field lines with opposite polarity come into close contact and realign, releasing energy in the form of heat and accelerated particles. Observations indicated that reconnection events in the heliosheath could produce sudden local temperature increases of 5,000–10,000 degrees and sharp bursts of energetic electrons. These localized events are small in scale relative to the entire heliosheath, but are fundamental for understanding energy transfer in low-density plasma. Density measurements highlighted another unexpected feature. The heliosheath is not uniform. Electron densities fluctuated between 0.001 and 0.004 electrons per cubic centimeter, and ion densities varied in tandem. Voyager 1 recorded a particularly dense patch at approximately 110 AU, where the density briefly spiked to 0.004 electrons, cm cubed, creating a localized plasma wall that coincided with a peak in magnetic field strength. Voyager 2 observed similar structures but at slightly smaller distances, reinforcing the notion that the heliosheath is highly structured and influenced by the asymmetric pressure of the interstellar medium. The interaction between solar wind and interstellar neutral atoms was also evident. Voyager detected energetic neutral atoms originating in the heliosheath, produced when ions from the solar wind collided with neutral interstellar hydrogen. ENAs, traveling at hundreds to thousands of kilometers per second, provide a remote sensing window into the heliosheath's structure. By measuring fluctuations in ENA flux, Voyager helped map regions of high turbulence and particle acceleration, complementing the in situ plasma and magnetic field observations. These ENAs confirmed theoretical predictions that the heliosheath is a highly interactive environment where particles, fields, and neutral atoms exchange energy continuously. Voyager data revealed that the heliosheath's magnetic field is not only turbulent but also sectorized. The spacecraft detected alternating zones of magnetic polarity separated by the warped heliospheric current sheet. Edward Stone, who led the Voyager mission science team, noted that the width of these sectors increased with distance, reaching tens of millions of kilometers. These sectors create alternating regions of particle trapping and streaming, further adding complexity to the heliosheath structure. In some regions, ion fluxes dropped by 20–30% when the spacecraft crossed into a different sector, demonstrating how magnetic topology directly influences particle behavior. Temperature variations within the heliosheath also shed light on energy distribution. While proton temperatures averaged around 70,000 degrees, electrons were generally cooler, between 20,000 and 30,000 degrees. This two-temperature plasma persists due to the low collisionality of the medium, meaning ions and electrons exchange energy very slowly. Voyager's measurements confirm that magnetic turbulence and reconnection, rather than direct collisions, dominate energy transfer in this extreme environment. Voyager's observations also highlighted large-scale asymmetry in the heliosheath. The spacecraft recorded a heliosheath thickness of approximately 35 AU in the northern hemisphere, but only about 27 AU in the south, suggesting that interstellar pressure compresses the southern portion. Combined with variations in magnetic field orientation and solar wind pressure, this asymmetry helps explain why the termination shock and heliopause are not concentric shells, but rather elongated, irregular boundaries. Even particle acceleration showed asymmetry. Voyager 1 detected bursts of anomalous cosmic rays predominantly at 115, 120 AU, while Voyager 2 observed similar bursts slightly closer, between 100 and 510 AU. These discrepancies indicate that particle acceleration efficiency varies with the local magnetic and plasma environment. Researchers like Nathan Schwadron and Meravofa have used this data to improve 3D models of heliospheric particle propagation, showing that the combination of magnetic folds, turbulence, and sector crossings shapes how particles gain energy and eventually escape into interstellar space. Voyager's long-term monitoring also revealed temporal variability. Over periods of months to years, the heliosheath's density, magnetic field strength, and particle fluxes fluctuated in response to changes in solar activity. Coronal mass ejections, which left their imprint in the inner heliosphere, eventually propagated into the heliosheath, producing transient enhancements in magnetic field strength by 10–20% and particle fluxes by up to 50%. This confirmed that even at distances of over 100 AU, the Sun continues to influence the heliosheath in subtle but measurable ways. Voyager data showed that energy, turbulence, and particle populations evolve as the spacecraft approached the heliopause. Magnetic barriers compress, folds become tighter, and plasma temperatures reach upwards of 90,000 degrees in localized regions. Rewriting the maps, what the wall tells us about the heliosphere. Voyager 1 and Voyager 2 reached the extreme limits of the heliosphere. The discovery of the 50,000-degree wall, a high-temperature plasma region at the edge of the heliosphere, provided new measurements that challenged previous models of heliospheric structure. Voyager's instruments provided a perspective on the heliosphere's outer structure. The spacecraft's plasma detectors, magnetometers, and cosmic ray instruments recorded detailed measurements as the probes moved beyond 100 astronomical units from the Sunday. These observations revealed that the heliosphere was far from uniform. Voyager 1, which crossed the heliopause at approximately 121 AU in 2012, observed plasma densities rising from 0.002 electrons per cubic centimeter in the inner heliosheath to 0.08 electrons per cubic centimeter in the outer regions. Voyager 2, following a similar path but slightly closer to the solar equator, crossed at 119 AU, revealing variations in magnetic field orientation and plasma compression that confirmed the heliosphere was not a perfect sphere. Measurements highlighted the asymmetry of the solar bubble. The southern hemisphere appeared compressed, pushed inward by the local interstellar magnetic field, while the northern hemisphere was elongated, trailing opposite the solar system's motion through the galaxy. Models derived from Voyager data indicated that the heliosphere's boundary was determined by a combination of the solar wind, interstellar magnetic pressures, and the density of surrounding interstellar plasma. The termination shock, where the supersonic solar wind slows to subsonic speeds, appeared at different distances depending on latitude, roughly 84 AU in the south and 94 AU in the north. Magnetic field data provided additional insight. Voyager's magnetometers recorded a spiral pattern that became increasingly twisted near the heliopause, with intensities reaching 0.3 nanoteslars, 10 times stronger than near Earth. These spirals were not smooth. Voyager observed kinks, folds, and regions of turbulence that acted as barriers, redirecting solar wind particles and cosmic rays. Magnetic turbulence formed channels and eddies, creating a patchwork of high and low particle fluxes across the heliosphere. Voyager's cosmic ray subsystem recorded changes in energetic particle flux. As the spacecraft approached the heliopause, cosmic ray intensity doubled for particles in the 100-500 MeV range. These measurements, taken between 2005 and 2012, provided quantitative data on how the Sun's magnetic field affected galactic cosmic rays. The cosmic ray flux was not uniform, with directional anisotropies indicating that some regions of the heliopause allowed deeper penetration. Voyager 2's crossing 3 years later confirmed these anisotropies, showing that the Sun's influence varied with distance, latitude, and local magnetic topology. Energetic neutral atoms offered another layer of mapping. When solar wind ions collided with interstellar neutrals, they were neutralized and sent back across the heliosphere. Voyager's low-energy charged particle instrument detected bursts of these particles, allowing scientists to infer regions of high interaction between solar and interstellar matter. Later, the Interstellar Boundary Explorer mission confirmed the presence of a ribbon of ENAs, a narrow, elongated band stretching across the heliosphere. This ribbon aligned with Voyager's observations of plasma turbulence and magnetic compression, providing a crucial piece in understanding the structure of the solar system's boundary. Temperature measurements from Voyager provided data on plasma conditions. The 50,000-degree wall indicated a region of high plasma heating caused by compression and acceleration of particles as the solar wind collided with the interstellar medium. Electron temperatures in the inner heliosheath were recorded at tens of thousands of degrees, while ion temperatures spiked near the heliopause. Voyager's plasma wave instrument, or PWS, detected oscillations corresponding with local density changes and heating mechanisms. Plasma, magnetic, and particle data were used to create a three-dimensional map of the heliosphere. The outer boundary was not a smooth sphere. Models depicted an elongated, asymmetric bubble with regions of compression, turbulence, and magnetic distortion. Voyager 1's crossing of the heliopause in the northern hemisphere and Voyager 2's crossing in the south showed latitudinal asymmetry and variations in heliospheric thickness, with estimates ranging from 1 to 10 AU, depending on local solar and interstellar conditions. Data from Voyager informed models for stellar wind bubbles around other stars. Observations of asymmetry, turbulence, and particle acceleration were used to predict the extent to which exoplanets might be shielded from galactic cosmic rays. Stars with stronger magnetic fields or higher stellar wind output could produce more extended bubbles, while stars in denser regions of the galaxy might have compressed heliospheres, exposing planets to higher radiation levels. Data from Voyager revealed temporal variations in the heliosphere. Solar activity cycles, including periods of solar maximum and minimum, caused expansions and contractions of the outer bubble. During the solar maximum of 2000-2001, Voyager detected compressions of up to 5 AU in the Helios heath, while solar minima allowed interstellar material to penetrate further inward. Voyager identified channels and preferential pathways in the Helios sheath. The spacecraft recorded directional anisotropies in particle fluxes, showing regions where cosmic rays could more easily penetrate toward the inner solar system. These channels were associated with draping of magnetic field lines over the heliopause, forming corridors of lower resistance surrounded by regions of higher magnetic density. Data from Voyager combined plasma wave measurements, magnetic field readings, energetic particle data, and cosmic ray observations to correlate density fluctuations, temperature spikes, and particle accelerations. For example, sudden increases in plasma density detected by the PWS coincided with enhanced magnetic turbulence and localized spikes in cosmic ray intensity. The maps informed models of particle acceleration, magnetic reconnection, and turbulence in plasma environments. Voyager's data have been used in simulations to predict heliosphere behavior under various solar and galactic conditions. Voyager provided the first three-dimensional, high-resolution view of the solar system's edge, quantified temperature, density, and magnetic variations, and recorded interactions between solar and interstellar forces. The heliosphere was observed as a measurable region of space, with contours, turbulence, and boundaries detectable with available instruments. Comparing other stars, the universe's many bubbles. The Sun's heliosphere, now meticulously mapped by Voyager, is just one example of a star carving out a bubble in the interstellar medium. Across our galaxy, every star with a stellar wind generates a protective envelope, though the size, shape, and dynamics vary dramatically depending on the star's properties and its galactic environment. Observations of these stellar bubbles allow astronomers to study variations in space weather around planets light years away. Massive stars, for instance, generate stellar winds far stronger than the Sun's. Stars like Betelgeuse in the Orion constellation eject material at speeds of 10 to 20 kilometers per second, forming vast bubbles thousands of astronomical units across. Infrared observations from the Herschel Space Observatory revealed a spectacular bow shock surrounding Betelgeuse, where its supersonic wind collides with the interstellar medium. The shock compresses gas and dust, creating temperatures in excess of 50,000 Kelvin at the interface, remarkably similar to the temperature observed at the 50,000-degree wall at the edge of our heliosphere. Unlike our Sun, however, the intense radiation and mass loss of these supergiants create highly asymmetric bubbles, often elongated in the direction of their motion through the galaxy. Even stars, smaller than the Sun, can generate heliosphere-like structures. Red dwarfs, which constitute about 75% of the stars in the Milky Way, have much weaker winds, typically around 200 to 400 kilometers per second. Observations of Proxima Centauri, our nearest stellar neighbor, indicate that its stellar wind produces a bubble roughly 50 AU, in radius only half the size of our Sun's heliosphere, yet still capable of deflecting a significant fraction of high-energy particles. Binary star systems provide another intriguing case. In these systems, two stars orbit each other, and their winds interact to form complex, intertwined bubbles. The Alpha Centauri system, composed of Alpha Centauri A and B, is an example where overlapping heliospheres create regions of compression and turbulence. Computer simulations, calibrated with Voyager's heliosphere data, suggest that such binary interactions produce regions of shock and enhanced magnetic fields, leading to irregular structures that are constantly reshaped as the stars orbit each other. In some cases, the overlap may allow cosmic rays to penetrate deeper into the system than around a solitary star, highlighting how star type and arrangement directly influence local space conditions. Observations of stellar bubbles also shed light on the life cycle of stars. When a star enters its final evolutionary stages, the bubble can expand dramatically. Planetary nebulae, formed when medium-sized stars shed their outer layers, are surrounded by shells of ionized gas extending up to a light-year from the star. These shells, detectable in optical and radio wavelengths, are far larger than our heliosphere, yet they share key physical principles: a central stellar wind pushing against interstellar material, shock fronts forming at the boundary, and regions of high-temperature plasma. The motion of stars through the galaxy also affects the shapes of their bubbles. The Sun travels at approximately 828,000 kilometers per hour relative to the local standard of rest. This motion creates a tail in the heliosphere, the heliotail, stretching thousands of AU downstream from the Sun's path. Other stars, moving at different speeds and through regions of varying interstellar density, produce bow shocks of differing intensity. Runaway stars like Zeta Ophiuchi, moving at nearly 24 kilometers per second through a dense interstellar cloud, generate bow shocks visible in infrared light, spanning several light-years. These observations indicate that the shape of a stellar bubble depends not only on the star's wind, but also on its speed and the density of the surrounding interstellar medium. Comparing stellar bubbles also provides insight into cosmic ray modulation. Voyager revealed that the heliosphere slows and deflects galactic cosmic rays, particularly at the termination shock and heliopause. Similarly, massive stars with strong winds create extended regions where cosmic rays are diverted or accelerated. In star-forming regions like the Orion Nebula, overlapping stellar winds create turbulent cavities that can either trap or channel energetic particles. These processes affect the local radiation environment around stars. Technological observations have expanded our view of these bubbles. The Hubble Space Telescope, Chandra X-ray Observatory, and ESA's Gaia mission have mapped stellar motions, wind speeds, and interstellar interactions with remarkable precision. For instance, Gaia data allowed astronomers to estimate that the heliosphere is currently moving into a slightly denser interstellar cloud, the local interstellar cloud, with a density of roughly 0.3 hydrogen atoms per cubic centimeter. This cloud is only a small fraction denser than the surrounding medium. Yet even minor differences affect the size and shape of the heliosphere, demonstrating that small interstellar variations can have measurable consequences for stellar bubbles. Some stellar bubbles are influenced by multiple phenomena simultaneously. Fast-moving neutron stars, for example, leave behind pulsar wind nebulae, where relativistic particles and magnetic fields create highly energetic bubbles that shine in X-rays and gamma rays. These structures, observed in the Crab Nebula and Vela pulsar, differ from the Sun's heliosphere and are formed by a central source generating an extended, energized envelope. Even within similar stars, the local environment creates variation. Comparative studies show that two Sun-like stars can have heliospheres differing in size by as much as 50%, primarily due to differences in surrounding interstellar pressure. Stars embedded in denser clouds have compressed bubbles, while stars in lower density regions can produce larger, more elongated structures. This variability underscores the importance of direct measurements, like those provided by Voyager, to accurately model the interaction between stellar winds and the interstellar medium. The study of stellar bubbles also informs our understanding of supernova remnants. When massive stars end their lives in supernova explosions, they leave behind rapidly expanding shock waves that interact with previously existing stellar wind bubbles. Observations of remnants like Cassiopeia A show regions where the shock wave collides with dense wind material, producing localized heating exceeding millions of degrees and accelerating cosmic rays to near-light speeds. In recent years, advanced simulations have integrated Voyager data with multi-wavelength astronomical observations to create a detailed library of stellar bubbles across the galaxy. These simulations reveal patterns. Faster stellar winds produce more elongated structures, higher interstellar densities create compressed shock fronts, and the interplay of multiple stars can generate turbulent cavities and corridors for energetic particles. By comparing these simulations with actual data, astronomers can estimate stellar wind conditions, radiation levels, and magnetic shielding around exoplanets. Magnetic fields, particle acceleration, plasma heating, and shock formation occur wherever a star interacts with its galactic surroundings. Voyager's exploration of the outer heliosphere provided the first in situ measurements of these processes, allowing comparison with phenomena around other stars. Stars move through the galaxy, interact with interstellar clouds, and evolve over millions of years. Their bubbles expand, contract, and sometimes merge, affecting the local interstellar medium and nearby star-forming regions. Voyager provided data on the heliosphere's structure, temperature, and particle fluxes, which helps model interactions between stellar winds and the interstellar medium. Comparisons of the Sun's heliosphere with other stellar bubbles provide data on the galaxy's magnetic and plasma environment. Voyager's measurements offer precise observational data to test theoretical models. The next frontier, designing missions beyond Voyager. Even as Voyager continues its mission, the scientific community is planning the next generation of spacecraft to explore the outer solar system and interstellar space. Voyager provided the first direct measurements of the heliopause and interstellar medium, but its instruments are decades old and limited in bandwidth. Designing missions to exceed Voyager requires updating spacecraft engineering, propulsion, communication, and scientific instrumentation to gather higher resolution data over larger distances. One of the primary considerations for future interstellar missions is propulsion. While Voyager relied on gravity assists from Jupiter and Saturn to gain speed, future probes must achieve even higher velocities to reduce travel times to hundreds or thousands of astronomical units. NASA's proposed interstellar probe, for instance, would use a combination of a high-energy chemical launch and a Jupiter gravity assist, targeting speeds of approximately 20-25 kilometers per second, roughly 1.5 times faster than Voyager 1. Alternative propulsion concepts such as solar sails, ion drives, and nuclear thermal propulsion are also under evaluation. A solar sail, for example, could leverage concentrated sunlight or even laser beams to accelerate a small spacecraft to speeds of up to 100 kilometers per second, potentially reaching the outer heliosphere within 15 years. Another critical factor is the spacecraft's power source. Voyagers relied on radioisotope thermoelectric generators to supply steady power over decades. For new missions, improved RTGs or next-generation nuclear batteries are being considered, capable of delivering higher power outputs with reduced mass. The kilopower reactor concept, a small fission reactor under NASA development, could provide hundreds of watts of electricity continuously, sufficient to operate advanced instruments and communication systems far beyond the Sun's influence, where solar panels are ineffective. Communication remains a formidable challenge. Voyager transmits at rates of only 160 bits per second from interstellar distances. Future missions will need high-gain antennas, advanced error-correcting protocols, and perhaps laser communication systems capable of gigabit per second data rates across billions of kilometers. Laser communication, using narrow, coherent light beams, can potentially increase data throughput by factors of 10,000 compared to traditional radio systems, although pointing accuracy must be maintained to fractions of a microradian to ensure the beam reaches Earth-based receivers. Missions like the Deep Space Optical Communications Project have already demonstrated this technology on spacecraft, such as the Lunar Laser Communication Demonstration, proving its feasibility for interstellar applications. Scientific payloads for next-generation probes must also evolve. Voyager carried 11 instruments focused on magnetism, plasma, cosmic rays, and imaging. Future spacecraft will carry miniaturized spectrometers capable of analyzing interstellar dust and gas composition in real time, advanced magnetometers with picotesla sensitivity, and high-resolution plasma wave detectors to capture fine-scale turbulence in the heliopause. Imaging instruments may include hyperspectral cameras to detect variations in interstellar light, mapping the distribution of neutral hydrogen, helium, and heavier elements. The interstellar probe concept, for instance, includes dust analyzers capable of measuring particle sizes down to a micron and mass spectrometers to identify isotopic ratios important for understanding the galactic environment's chemical evolution. Trajectory planning is another challenge. Beyond simple gravity assists, mission designers must account for the interstellar medium's structure, including regions of higher particle density, magnetic field fluctuations, and cosmic ray hotspots. Simulations based on Voyager 1 and 2 data suggest that certain regions of the outer heliosphere experience particle fluxes several times higher than previously predicted. Understanding these variations helps engineers design shielding that balances mass constraints with the need to protect sensitive electronics from energetic particles. Materials such as aluminum tungsten alloys and advanced ceramics are under consideration for micrometeoroid and cosmic ray shielding. Data management and onboard autonomy are increasingly critical. Voyager depends heavily on Earth-based operators for commands, but future probes operating thousands of AU away will experience signal delays of several days to weeks. Autonomous decision-making, including dynamic instrument scheduling, anomaly detection, and adaptive orientation control, is essential. Modern spacecraft can incorporate artificial intelligence to adjust their observation plans in real time, for instance, increasing measurement frequency during sudden cosmic ray bursts or plasma fluctuations. Such autonomous systems reduce reliance on Earth intervention while maximizing scientific return. Interstellar missions also face thermal management challenges. Voyager's RTGs generate heat that must be carefully dissipated, but spacecraft traveling beyond the heliosphere encounter extremely low ambient temperatures, around 3 Kelvin, the background temperature of the cosmic microwave background. Advanced insulation materials, radiative coatings, and small heat pumps will be essential to maintain instruments within operational ranges. Thermal stability is particularly important for optical instruments, as even slight variations can distort measurements of plasma wave activity or interstellar dust composition. Future missions will probe the local interstellar cloud, or LIC, that surrounds our solar system. Voyager data suggest that the LIC has a density of about 0.1 atoms per cubic centimeter and is threaded with magnetic fields around 0.5 nanoteslas. Future probes could map the three-dimensional structure of this cloud, revealing its turbulent boundaries, density gradients, and interactions with other interstellar clouds. These measurements provide data for heliophysics studies and broader astrophysical questions, such as the propagation of cosmic rays, the origin of galactic magnetic fields, and the formation of interstellar structures. Future missions may also include the capability to study interstellar neutral atoms, which Voyager indirectly observed through plasma wave measurements. Advanced neutral atom detectors can determine the velocity distribution, composition, and origin of these particles, providing insight into how material flows from the galaxy into our solar system. Combined with cosmic ray detectors, such measurements would allow scientists to reconstruct a comprehensive picture of interstellar particle dynamics. Even the question of longevity is central to mission design. Voyager has lasted over 46 years, but future missions are expected to operate for decades longer, to traverse distances up to 1,000 AU. Engineers must address component degradation from radiation, micrometeoroid impacts, and thermal cycling. Redundant systems, radiation-hardened electronics, and self-healing software protocols are all under consideration to ensure that these spacecraft remain operational long enough to provide meaningful science across decades. International collaboration will support these missions. Data from Voyager have been used by agencies worldwide, including ESA, JAXA, and CNSA, in planning interstellar studies and solar system exploration. Pooling resources allows nations to share costs for developing advanced instruments, deep space communication infrastructure, and high-velocity launch technologies, facilitating more efficient mission planning. Moreover, planetary flybys may still be relevant, even for interstellar missions. A Jupiter or Saturn gravity assist can increase spacecraft speed without additional fuel, reducing travel times to interstellar space. Detailed observations during these flybys, using cameras and spectrometers, can also capture updated planetary data, supplementing Voyager's decades-old measurements. For example, an interstellar probe passing Jupiter could measure its magnetosphere, radiation belts, and high-energy particle flux with modern instruments, offering a temporal comparison to Voyager's legacy datasets. The design philosophy for missions beyond Voyager balances robustness with adaptability. Engineers aim for modular spacecraft, allowing instruments to operate independently even if others fail. This approach ensures continued operation under uncertain interstellar conditions. Additionally, modularity allows future missions to include instruments that may not yet exist, such as quantum sensors capable of detecting minute magnetic or gravitational anomalies in deep space. Finally, public engagement and educational outreach continue to be considered in mission planning. Voyager included the Golden Record and captured planetary flybys. Future interstellar probes may carry messages as cultural artifacts. Outreach programs can utilize real-time data visualization, virtual simulations of interstellar space, and interactive platforms to provide educational content and maintain public interest in space missions. The interstellar medium, the ocean between stars. Beyond the heliopause lies a vast and largely invisible ocean, the interstellar medium, or ISM. This region is not empty, despite the seeming void between stars. It is a tenuous mixture of gas, dust, cosmic rays, and magnetic fields that fills the space between solar systems, stretching across the galaxy in complex patterns shaped by stellar winds, supernova explosions, and galactic dynamics. Voyager 1 and 2, having crossed the boundary into interstellar space, provided the first direct measurements of this environment, including plasma density, particle flux, and magnetic field data. The density of the ISM is extraordinarily low by terrestrial standards. The local interstellar cloud, through which our solar system is currently moving, has an average density of roughly 0.3 atoms per cubic centimeter, mostly hydrogen, with small amounts of helium and trace heavier elements. By comparison, Earth's atmosphere contains around 10-19 molecules per cubic centimeter, illustrating just how sparse this environment is. Yet, despite its low density, the ISM carries immense energy and structure, forming filaments, bubbles, and shock fronts across distances of light years. Voyager's plasma wave instruments measured fluctuations in electron density ranging from 0.05 to 0.2 electrons per cubic centimeter, confirming that the local interstellar medium is dynamic, not uniform. Temperature in the ISM is another remarkable factor. Voyager's instruments detected plasma temperatures around 7,000 Kelvin in the local interstellar cloud, significantly hotter than expected from neutral gas estimates. Elsewhere in the galaxy, temperatures can vary widely, from a few tens of Kelvin in dense molecular clouds to millions of Kelvin in the hot interstellar gas created by supernova remnants. These temperature differences, combined with varying densities and magnetic field strengths, result in turbulence and pressure gradients that influence ISM structure and particle motion. Magnetic fields thread through the interstellar medium, exerting subtle yet powerful influences. Voyager detected local interstellar magnetic field strengths of about 0.5 nanoteslas, roughly 100,000th of Earth's magnetic field. These fields guide charged particles, shape plasma waves, and contribute to the overall structure of the ISM. On galactic scales, magnetic fields are critical in star formation, as they can slow the collapse of gas clouds or channel material along specific direction. The interplay between magnetic fields and charged particles also affects cosmic ray propagation, influencing how high-energy particles traverse the galaxy before interacting with planetary systems like our own. Cosmic rays themselves are a defining feature of the interstellar medium. These high-energy particles, mostly protons, with a smaller fraction of heavier nuclei and electrons originate from supernova explosions, pulsars, and other energetic phenomena. Voyager's cosmic ray subsystem recorded a significant increase in galactic cosmic ray intensity beyond the heliopause, with proton fluxes up to 4 times higher than inside the heliosphere. Measurements confirm the role of the heliospheric magnetic field in modulating cosmic ray flux, with lower intensities inside the heliosphere compared to the local interstellar medium. Interstellar dust is another key component of this vast ocean. Tiny grains of carbon, silicates, and ices, typically a few micrometers in size, drift through the ISM. While sparse on the order of 1 grain per cubic meter, they are critically important for chemical reactions, molecule formation, and star and planet formation. Voyager's plasma science instrument detected the influence of dust on plasma waves, confirming that even individual micrometer-sized particles can interact with the interstellar environment in measurable ways. Some of these grains eventually find their way into our solar system, becoming meteoroids or contributing to zodiacal light, linking the ISM directly to planetary phenomena. The ISM is far from homogeneous. It consists of multiple phases: the hot ionized medium, with temperatures of 1 to 10 million Kelvin, the warm ionized and neutral medium, with densities around 0.2–0.5 particles per cubic centimeter, and cold molecular clouds, with densities reaching up to 1 million particles per cubic centimeter. Voyager traversed the warm local interstellar cloud. Shock waves from supernovae propagate through the ISM, compressing gas and triggering star formation in molecular clouds. Stellar winds from massive stars carve cavities, creating bubbles of low-density, high-temperature plasma. These dynamic processes produce turbulent motions, with velocities in the tens of kilometers per second, influencing the chemical and physical environment of stars and planetary systems. Chemical composition in the interstellar medium provides clues about the life cycle of matter in the galaxy. Voyager detected elements such as hydrogen, helium, oxygen, nitrogen, and heavier species, including iron and magnesium in the local cloud. By measuring ionization levels and isotopic ratios, scientists can trace the origins of these elements, linking them to previous generations of stars. For instance, isotopic ratios in interstellar oxygen and neon suggest enrichment from nearby supernovae within the last few million years, showing that the solar system is moving through a region affected by past stellar explosions. The ISM supports waves and turbulence that propagate through the plasma. Voyager recorded plasma oscillations at frequencies of a few kilohertz, caused by variations in electron density and magnetic field orientation. This turbulence affects particle propagation, energy transfer, and the formation of structures on scales ranging from astronomical units to parsecs. The ISM also interacts directly with the heliosphere. The heliosphere itself is a bubble carved into this medium by the solar wind, which slows, deflects, and heats the surrounding interstellar plasma. Voyager data have shown that the heliosphere is asymmetric, likely due to differences in local magnetic field orientation and interstellar density. Observations of these interactions provide measurements of plasma compression, deflection, and heating at the heliospheric boundary. Dust, gas, magnetic fields, and cosmic rays form a network that extends over light years. The motions of these components are influenced by supernovae, stellar winds, and galactic rotation, creating large-scale flows. Voyager observed evidence of such flows through the directionality of incoming neutral atoms and magnetic field orientation. These flows can reach hundreds of kilometers per second relative to the Sun, affecting the motion of the solar system within the local interstellar medium. Light propagates through interstellar gas and dust, producing reddening, extinction, and scattering effects that influence astronomical observations. Cosmic rays interact with interstellar material, generating gamma rays and neutrinos detectable across vast distances. Voyager's in situ measurements, combined with astronomical observations, are used to calibrate models of galactic structure, star formation, and chemical evolution. In addition, the interstellar medium contains low-density, high-temperature plasma with embedded magnetic fields, turbulence, and shock fronts spanning light years. Voyager's measurements of plasma waves, particle densities, and magnetic fields provide benchmarks for simulations, allowing scientists to study processes such as magnetic reconnection, turbulence cascades, and particle acceleration relevant to astrophysics, fusion research, and space weather modeling. Interstellar probes encounter cosmic rays, interstellar dust, and magnetic turbulence when traveling beyond the heliosphere. Data from Voyager provide measurements of particle flux, plasma density, and magnetic field variations that inform spacecraft shielding, instrument design, and navigation strategies. Voyager's dual mission, science and signal from interstellar space. Even as Voyager 1 and 2 glide through the interstellar medium, far beyond the protective bubble of the heliosphere, they carry the golden record. The Voyager spacecraft travel at roughly 17 kilometers per second, faster than any man-made object before them. At this speed, Voyager 1 would take about 296,000 years to reach Proxima Centauri, the nearest star, if it were headed directly there. Despite the vast distances, Voyager continues to send information back to Earth. Its communications rely on the Deep Space Network, a global array of antennas in California, Spain, and Australia. Even at over 23 billion kilometers from the Sun, the spacecraft's 20-watt transmitter sends data, though signals take more than 21 hours to travel one way. Engineers on Earth detect these signals using antennas as large as 70 meters in diameter, capturing particle and field measurements from the edge of the Sun's influence. Data include plasma densities and cosmic ray intensities. Voyager's instruments continue to reveal the environment beyond the heliopause in unprecedented detail. The plasma wave subsystem measures electron density variations, detecting fluctuations as small as 0.01 electrons per cubic centimeter. The cosmic ray subsystem captures the intensity of galactic cosmic rays, showing increases of nearly 30% compared to levels within the heliosphere. The magnetometers monitor interstellar magnetic fields at strengths around 0.5 nanoteslas, providing crucial information about how the local interstellar cloud is structured and how it interacts with the heliosphere. Together, these instruments allow scientists to study the interstellar environment in situ, rather than relying solely on telescopic observations from within the solar system. The Golden Record is a cultural artifact. Its contents were selected under the guidance of Carl Sagan, Frank Drake, and Ann Druyan to represent Earth's diversity. It includes greetings in every major language, traditional music from every inhabited continent, natural sounds such as thunder, whales, and birdsong, and encoded images of human anatomy, landscapes, and technological achievements. Signals from the spacecraft, traveling at the speed of light, take decades to reach Earth. The images and measurements received today were taken years earlier. The Golden Record was designed as a time capsule, intended to communicate information about humans to any potential extraterrestrial civilization. Scientific data and symbolic communication converge in a practical sense as well. Voyager's instruments allow the monitoring of the interstellar medium's conditions, informing future missions about the challenges of traveling beyond the Sun's protective bubble. The spacecraft measures high-energy cosmic rays that can damage electronics, interstellar dust that can erode surfaces over decades, and subtle plasma variations that may affect long-duration spacecraft systems. This information is critical for the design of next-generation probes, such as the proposed Interstellar Probe mission, which aims to travel 1,000 astronomical units from the Sun within the next century. Voyager's ongoing measurements provide the baseline for understanding what humans may encounter when venturing deeper into the galaxy. Communication across such immense distances requires precision engineering. Voyager's transmitters operate at the S-band and X-band frequencies, using highly directional antennas to focus signals toward Earth. The spacecraft's 3.7-meter high-gain dish is pointed with accuracy, accounting for slight changes in orientation caused by sunlight pressure, gravitational influences from planets, and thermal expansion. Engineers on Earth compensate for the Doppler shift caused by Voyager's motion relative to Earth, about 3.6 kilometers per second per year. Each transmission requires precise coordination of physics, engineering, and timing to ensure information reaches Earth. The spacecraft were launched in 1977 with instruments and electronics designed to operate for a decade. More than 45 years later, they continue to function. Radioisotope thermoelectric generators provide a steady power source, declining by about 4 watts per year as the plutonium-238 decays. Scientists from multiple countries analyze Voyager's measurements, comparing plasma densities, magnetic fields, and cosmic ray intensities to models and observations from Earth-based instruments. The European Space Agency, NASA centers, and universities worldwide participate in decoding the messages from the spacecraft. These observations make the interstellar environment measurable and shared across continents. The Golden Record, the spacecraft design, and the communication systems were conceived at a time when computers were measured in kilobytes, not terabytes, and when planetary exploration was still in its infancy. These design decisions allowed Voyager to function beyond its expected lifespan, sending data from a region of space previously unobserved. The challenge of communicating across 23 billion kilometers inspired developments in low-noise amplifiers, antenna design, and data compression techniques. These technologies have applications beyond space exploration, including telecommunications and remote sensing on Earth. As Voyager drifts farther into interstellar space, it encounters regions of varying plasma density, magnetic turbulence, and cosmic ray intensity. Its instruments measure electron density oscillations on the order of 0.01 electrons per cubic centimeter and galactic cosmic ray fluxes that fluctuate with solar activity. These measurements allow scientists to map the local interstellar environment in 3 dimensions. The message from Voyager is not limited to the Golden Record. Scientific data sent back to Earth reveal the structure, composition, and dynamics of the galaxy. The Sun no longer dominates the spacecraft's environment, and Voyager continues to transmit measurements across interstellar distances. Voyager continues to operate decades after its launch, providing data from regions of space beyond the Sun's influence. The Golden Record carries encoded information about Earth and its inhabitants, while the spacecraft's instruments collect measurements of the interstellar medium, including plasma waves, cosmic rays, and magnetic fields.